Okay, so the next few segments I want to spend talking about NoSQL. And so these systems are typically associated with building very large scalable web applications as opposed to analyzing data, which is really the focus of this course. However, I think it's important to cover this topic for a few reasons. One is, as a data scientist, you'll be manipulating data that is increasingly found in one of these variants of a NoSQL system. But also the systems and the terminology in this space are really influencing people's thinking about how to deal with large-scale data. And so being cognizant of the landscape here and being cognizant of the major trends in the history allow you to make informed decisions about this. As a data scientist, you may be asked to make recommendations about what kind of platform to go with to do your analysis. And so understanding the pros and cons of some of these systems and how they work can be pretty important. Okay. And then maybe third, the same concepts that we've been discussing in other segments, sort of relational algebra, logical data independence, simple analytics going a long way, simple scalable analytics, indexing. These ideas come up in this space as well. And so it's yet another application of these concepts. And then maybe finally, the data scientist may be called upon to actually build some of the large-scale systems as part of their work. It's not unheard of. I mentioned in the first few segments that building data products was an important part of data science, and so one manifestation of data products is some of these large-scale web applications. Okay, and so NoSQL systems may or may not be a part of that. Fine, so let's get started. All right, so where we are so far is we've mentioned that data science maybe has these three steps: data preparation at large scale. All right, and we've talked about manipulation and munging and data jujitsu and so on, and that's all this step one. And then step two is analytics, or actually running the model, and we're going to get to that in the next week. And then third is communicating the results, interpreting and communicating the results, and this will be visualization will be a big part of the way we talk about communication. Okay, so we're still in this data preparation phase, and we're spending a little bit longer on that than, say a third of the course, more than a third of the course, for the reason that I gave in the first few segments, that really this is the part that keeps people up at night. So I want to make sure that you're armed with how to use databases to do this data munging, how to use MapReduce to do this data munging. Also make the point that a lot of times even the analytics itself can be pushed into these systems, which you saw in hopefully in assignment 2, in the database assignment. Okay. So then some of the key ideas from databases that we took away were this concept of the relational algebra comes up even outside of databases. It's not only found, with SQL systems, and we'll see that again. And this notion of physical logical data independence comes up over and over again. Maybe indexing. And then we talked about MapReduce, and we gave a lot of examples of some basic operations in MapReduce, and we started an assignment involving writing your own MapReduce programs, at least at the programming model level. And so here we saw that part of the advantages of the system itself, first at Google and then in the implementation Hadoop, was fault tolerance at scale. And another one was you didn't have to load the data. You could just work with it as is, unlike databases where you have to actually impose some sort of a scheme on it in order to even touch it for the first time. And so that first step can be a doozy. Okay. Extending this point, direct programming on in-situ data. So anything that comes at you, you can if you can write a program that can process it, you can probably write a MapReduce program that can process it at scale. Right? And that's a very, very powerful thing. All right. Maybe another way to put this is sort of single developer, right? You're kind of up and running within the hour with MapReduce, and that was never really a property that databases had. It was always a sort of difficult, it was a significant project to get a database installed and running. Fine. So that's the background, but what we haven't talked about is this NoSQL system. And so I want to use this table as a way to sort of organize the roadmap for this discussion. And so what I've done here is tried to list out by feature a bunch of relevant systems in this space. And right now they're sort of sorted by time. And so these features are admittedly selected by me for what the important ones are, but I don't think they'd be too controversial, and I don't think there's anything obviously missing here either. Okay, so going through these briefly. Then a major one here was that it needs to scale to sort of thousands of machines. Then there's some need to look up by a primary index. What I mean by that is by some key value, right? You can look up by some record identifier. Okay, and then another feature that they may or may not have is the look up by secondary indexes. So what I mean here is you can look up by some attribute that is not that key. Okay, and so databases have this, for example. You can build an index on any attribute you want, and the optimizer will take advantage of it. The third one, and this is the one we'll spend a lot of time on because it's sort of pretty fundamental to the motivation for why NoSQL systems sort of earn their own moniker or are different, are transactions. Okay, and you can also see that there's some complexity here that I'll try to explain as we go through this. So it's not just a yes or no, it's kind of depends on the case by case. Okay, and then this field is whether or not these systems support essentially joins, but I've generalized that to analytics, and I'm perhaps guilty of making those two things almost synonymous. If you can do joins, then there's a whole space of different kind of analytics things you can do, and if you can't do joins, then you're leaving all that work up to the client, and all you can do is retrieve data. And so that's really a key indicator of how much computation you can push into the system and how much you have to sort of bring the data back out to the client. Okay. And then integrity constraints, and I debated about calling this schema instead of integrity constraints, but as I think we'll see, arguably some of these systems do indeed have a schema, but may or may not actually enforce that schema. And so it's, just to avoid the confusion, I'm going to call this integrity constraints. So this is sort of hard schemas, if you will. Okay. And then views, which if you remember is I'm declaring that to be synonymous with logical data independence. And then finally, is there some sort of declarative language or algebraic way of programming against this thing, or is it really just sort of a low-level, simple operation API? Okay. All right, so a couple of caveats here. One is I haven't included any parallel databases on this list at all, although there's absolutely no reason why you couldn't include them here. They would tend to have a lot of check marks across this row. But since the focus is NoSQL systems, I am leaving those out. And then the other caveat I make is that individual cells in this table may be debatable depending on how you interpret the columns. So this isn't necessarily meant to be hard and fast rules, but again, I don't think they'll be wildly controversial either. Okay. So one of the first stories you can tell by staring at this table is that relational databases, have been around for quite a while and have check marks sort of everywhere, have all these features, except they weren't really ever shown to scale to lots and lots and lots of computers, right? Everything was sort of on the order of tens of machines. Okay, so why don't they scale? Well, we talked in the MapReduce segment about sort of read performance and related, and sort of analyzed some experimental results from a paper in 2009 comparing sort of the benefits and strengths of MapReduce versus databases. So maybe on read performance there's an argument to be made that they did scale, but one area where they certainly didn't, or at least certainly weren't shown to scale to this level, was in updates. Okay, so not just the read and not just the analytic workload, but the transaction processing workloads. All right. Okay, so we start with the same schematic that we were looking at when we were talking about MapReduce and scalability, where we take a big data set and break it into chunks and send those chunks to different machines. Okay, and here we are replicating this chunk to 3 different machines, which is the same thing we did for the Hadoop file system for fault tolerance purposes, where if this machine dies, we still have 2 copies of the data to draw from, and we do this with every chunk. All right. But the two requirements we need to speak to here is we need to ensure high availability so that when something goes wrong, the data is still available. And we also want to support updates in this context, which is different than we were talking about before. So instead of just read performance or fault tolerance in the context of reads, we also want to make changes to this data now and have them propagate to both other replicas and in some cases to other consumers of that change, right? There might be other blocks of data that are refer to the same information. And I'll give you an example on the next slide. Okay, so imagine a social networking application where people are updating their status and their friends get to, your friends get to see your status updates. Okay, and so the write operation here is Sue updates her own status, and the question we ask is, of her friends, what happens? Who sees the new one? Who sees the old one? How does this status change propagate? And the answer to this question from a database perspective was, well, look, everyone must see the new change or no one does, right? Either the transaction commits and all copies of the data everywhere are synchronized simultaneously, and further, anybody attempting to read the value in an intermediate state is able to either read only the old value or has to wait until the transaction commits, right? Which could be an arbitrary, pretty long time. Deadlocks can happen, is why I said arbitrarily. Fine, so that's the answer given by databases. Everything's synchronous. Everything must be updated. It's either all or nothing. Okay. And the NoSQL system sort of made this observation that said, well, look, for really large applications, we simply can't afford to wait arbitrarily long for this to happen, right? I mean, you need status updates to be able to commit and respond so the user can go on and do other things, right? They can't sort of look at an hourglass while the synchronization is still occurring. And then further, the observation is, well, maybe it doesn't matter anyway. I mean, is it really that important that, here, if Sue's friend Joe sees the new status while Kai still sees the old status, maybe who cares, right? As long as Kai eventually sees the new status, maybe that's good enough. Okay, and so these observations suggested moving in a different area of the design space in sort of high scalability, high availability, and consistency, application consistency. And that motivated, that space of systems started to be associated with kind of anti-database, right? It took a very different approach than databases did, and so the term NoSQL came into play. It's actually unfortunate that the name that stuck was NoSQL, because it doesn't have all that much to do with SQL, right? It has more to do with the transaction processing side of databases, which is not all that relevant for SQL, right? I mean, the model of transactions is sequences of reads and writes, nothing to do with a query language. But hey, that's what stuck. Now, I don't mean to say that the term NoSQL only suggests these transaction models. It also sort of suggests a weaker data model and so on, and we'll talk a little bit about that. But I want this point to come across because this is one of the key ideas. Okay. How did databases solve this problem, or why did they take so long? Well, there's a protocol called two-phase commit that's fairly standard in these situations for synchronous processing. And so the motivation for why you want two-phase commit goes like this. If you want to have a bunch of replicas or other kinds of subordinates, anybody that wants to see the change, you make your status update and your friends need to see it. The server's holding those different friends need to be told of the change. And so if you just go ahead and tell them, say, look, I made this change, go ahead and update your internal state to reflect Sue's new status, then you could have, some of them report back success, but one of them could fail. But now you're in trouble, right? Because this one has the old value because it failed for some reason. Either you didn't hear back from the server at all, or it said, look, something's wrong with my disk, I can't do it, so it responds with a failure, regardless. And these two have already successfully applied I'll put a check mark, have already successfully applied the transaction. And so now you're in an inconsistent state. Subordinate 3 has the old value, and these guys have the new values. Okay? So how you solve this problem is two-phase commit. And so the first phase here is the coordinator sends a prepare to commit message, and the subordinates make sure they take action to make sure that they can commit that transaction when asked, no matter what. And so typically this means writing to a log the information related to the transaction, so that even if the power goes out, when they wake back up, they can pull it from the log. Okay. And then subordinates reply with a, yes, I'm ready to commit. And then in phase 2, if all the subordinates say they're ready, then you'll go ahead and send the commit message. And if anyone failed, instead anyone failed, then you send back an abort message, and the individuals can clean up. Okay. So this is fine. And here's a schematic of it. In step 1, they say prepare. These guys all write ahead to the log and say, I'm about to write this or I'm going to commit this transaction. They respond with, yes, I'm ready to do so. The coordinator comes back with commit, and then finally all the work is done. And I'm not going to show the schematic for what happens in a failure, but essentially the coordinator needs to watch out for it and send back an abort if something has gone wrong. Okay. Okay, so there's a couple of problems with this. One is there's some dependencies on the coordinator here that if the coordinator fails at the wrong time, things can go kind of screwy. And a fully distributed protocol for ensuring mutual commitment of transactions or other kinds of operations can be achieved, and one of the most successful and popular methods of doing this is an algorithm called Paxos that we're not going to talk about in detail, but you're going to see that term if you look at some of the readings for the NoSQL systems. Okay, so think two-phase commit on a local cluster for a database. Think Paxos for a distributed sort of peer-to-peer kind of protocol. And just briefly, what Paxos is essentially doing is it's a voting scheme. So people sort of vote on, the individual servers will have to self-determine whether or not they're supposed to commit the transaction or not. And the details can get a little bit subtle, but overall it's pretty simple given the difficulty of the task involved. Okay. So fine. So that's one problem. The other problem is just that with that Paxos sort of shares is that this can take a while, right? If subordinates don't respond promptly, you might be waiting around. If things fail multiple times, you need to sort of abort and retry transactions at the application layer, things can go slow. It doesn't necessarily scale when there's thousands or millions of subordinates that need to do this, you're kind of dead in the water. So other protocols that I'm not going to talk about in too much detail include multi-version, but you will see in some of the papers mentioned, multi-version concurrency control, where each write creates a new version of the data item, and the legality of a read is determined by checking the timestamp of the read transaction versus the current timestamp of the version that you're trying to read. Okay, and if it's been updated since the time you're supposed to be reading it, then prior to MVCC, all you could do is abort the read and say, look, you're looking at dirty data, you're done. But with multi-version concurrency control, you can actually keep multiple versions around and redirect the read to potentially to the prior version that is correct. Okay, and thereby aborting certain transactions. Fine. So that mechanism still has a dependency on a coordinator role to administer timestamps. A fully distributed scheme where the decision to go forward with the transaction or to abort a transaction is made through a voting scheme among peers is Paxos. And Paxos is very successful and very widely applied, and you'll see it mentioned in some of the NoSQL papers if you take the time to read them, and they're on the reading list. And so this relieves the dependency on having a central coordinator, but is still synchronous and still has the potential for deadlock and can take some amount of time to reach consensus depending on what's going on and what kind of failures are happening. And so it's difficult to guarantee very high performance and very low latency response times. All right. So then the term eventual consistency was originally defined not so much in the context of its utility in allowing systems to scale to very large levels, but just in this argument that the only players in distributed systems that could make the appropriate decision about how to handle conflicts were the applications themselves. And so it was a version of this end-to-end argument that you may or may not have come across in the context of networking. And so this was a paper in 1995 by Doug Terry where this term was coined. And so he says, we believe that applications must be aware that they may have read weakly consistent data and that their write operations may conflict with those of other users and applications, and that applications must be involved in the detection and resolution of conflicts, and so these naturally depend on the semantics of the application. And so we'll make the argument in a couple of segments that I'm not sure I totally agree with these assertions, that it actually is better for the system to take care of this when it can. But what I wanted to do is let you know that this is where the term comes from, as opposed to the NoSQL systems in the last 10 years or so, which is really where it increased in popularity. Okay, so what does it mean? Well, what it means is in the absence of updates, all replicas will eventually converge towards identical copies, right? So as long as things don't continuously change, as changes settle down, we'll all eventually see the same value, right? All your friends will see your status, right? They won't be permanently stuck looking at an old one. Okay. But, what the application sees in the meantime, what's one of your friends, which status one of your friends might be looking at, is really sensitive to the internal details of whatever application you're building, and is therefore difficult to predict. Okay, and so for this reason, it's a little bit difficult to reason very precisely or formally about what eventual consistency means, because it is so dependent on particular implementation details that are themselves difficult to formalize. Okay, and in general, contrast this with what we've been talking about with relational databases and things like Paxos, where they guarantee strong consistency, but there may be deadlocks. And so you can prove that no system can be free of deadlocks and guarantee consistency. And so relational databases and Paxos give up on this liveness property, meaning that they might allow deadlocks in favor of strong consistency. Now, you can show that the cases where deadlocks can occur can be made sort of rare through different design decisions, but they can still happen. Okay, fine. And so eventually consistent models say we can't afford the cost of waiting for these protocols to run, and moreover, they may not be necessary in certain application contexts. All right. So where we are now is we're looking at this column, and I've already sort of marked this up a little bit, but what these words now mean, and we'll talk about these a little bit more when we talk about a few of these systems, is the scope of where strongly consistent transactions are supported. And so the scope here of a single record means that I can update multiple fields in one record, and either all the changes will occur or none of them will occur. Okay. By the way, I filtered this list to only include NoSQL systems. So relational databases support this across arbitrary records, right? You can update a record over here and you can update a record over there and call that one transaction, and the system will only see both of those changes or neither of those changes. And that's what's not supported with these NoSQL systems. So within an individual record is supported. Within some of these systems, nothing's even supported. There's no guarantees at all, really. And what this EC means is eventually consistent. So it's not really strongly consistent. It's not a transaction, but they do have eventually consistent guarantees at the record level. And that's what all these systems sort of guarantee. And then this system Megastore that's based on Bigtable from Google, it's also a Google system, defines a notion of entity groups. And this is a set of related records for which transactions are strongly consistent for that group. Okay, so this is a little bit better than just one individual record is the only guarantee we can give, and it's a little bit less than any arbitrary record in the database. It's predefined entity groups that allow transactions. Okay, so this is sort of a compromise. Fine. And then this most recent system from Google, Spanner, offers true strong consistency across all the records, and we'll talk about why they made that choice in a little bit. Okay, so another concept I want you to be familiar with is this so-called CAP theorem from Eric Brewer in 2000, a follow-up paper by Lynch in 2002, where they define these three notions: consistency, availability, and partitioning. And the way this is often described is you have to choose two of these. You can't get all three. You have to choose two or sacrifice performance. But I don't really like thinking of it that way. And Eric Brewer has also sort of described that maybe that's not the right way to think about it. And the reason is because it's not clear what it means to choose consistency and availability at the expense of partitioning. Okay, so what is partitioning? Partitioning means, well, if you've got a big distributed system with hundreds of nodes involved, hundreds of servers all communicating with each other, and some segment of them lose communication with the other servers, can those two segments still make forward progress in the application independently and sync up later? Or does everything have to stop and wait, or certain nodes have to stop and wait in order to reestablish communication? So for example, if you have a master node that controls everything and you have some worker nodes that lose contact with the master, there are many designs at which you can't make any forward progress until you reestablish connections with the master node, right? You can do no useful work because you're waiting on communication. You're waiting on that last message from the master to tell you what to do next. So in those cases, you've given up availability, right? You go down, those nodes are no longer accessible or doing useful work in the context of a network partitioning. Okay. On the other hand, if you do say, well, sure, we're going to continue doing useful work even independently, then it's not difficult to show that you can arrive at an inconsistent state, right? Updates are coming into this partition and updates are coming to this partition of the network, and sometime down the road, communication is reestablished and you find out, oops, your replica has one value, my replica has another. Which one's right? Well, we're going to have to sort it out. But meanwhile, we've already sort of exposed these values to the application. So in some sense, we're demonstrably inconsistent. Okay. And so the point is you can't get all three of these. All right. So you've either sacrificed availability or you've sacrificed consistency by allowing things to continue working. So conventional databases essentially assume that there is no partitioning. And again, this is a function of them only operating on tens of nodes at a time, right? They didn't go to this sort of 1,000 node scale or planet-wide distributed systems. And so you could kind of assume that there wasn't really a need to worry about, well, what if queries are coming into half my nodes and they can't talk to the other half my nodes and so on. They're all sitting there in a cluster that's in your data center, or not even your data center, in your server room to some extent. And so that really wasn't an issue that they were thinking about too much. Okay. And the NoSQL systems do need to worry about this. They are very large. They are very distributed. There are different kinds of Byzantine failures happening all the time because of the sheer scale. And therefore, they choose to sacrifice consistency instead of availability. Okay. And so graphically, you can look at this in this sort of triangle form, and you can put different systems on sort of an edge here, where relational databases assume consistency and availability, but assume partitioning can never happen, while other systems need to tolerate partitioning but give up on availability. And they are ensuring that certain kinds of transactions are going to be consistent. Okay. And then other systems say, well, we're going to give up on consistency, but you can always do useful work. Okay. So fine. And really, this is the important thing here is that the scope of the transaction that I put in that table is sort of critical here too. It's not sort of nothing except for Spanner over here even tries to provide global transactions like relational databases do. Okay. All right. So fine. So I'll pick up here in the next segment. So Rick Cattell wrote a nice paper in 2010 about scalable SQL and NoSQL data stores, where he had a taxonomy of these systems and placed popular instances of these systems into that taxonomy. And so this slide corresponds to his grouping, where each color is one of the groups that he defined. So he sort of lumped them into key value stores, document stores, and extensible record stores. And so what he meant by that was a document is, an example of this is an XML document or the JSON object that we looked at in the Twitter assignment, where you can have sort of arbitrary nesting, and it's also extensible. You can add new things to it whenever you want. Okay, so no top-down schema being enforced. Okay, an extensible record you can think of as much like a database record, except that new attributes can be added. Okay, so there is some notion of a schema that's used for different various purposes, and in particular, there's sort of groups of attributes that are manipulated together, these families. But you can stick new attributes on an individual row, which you're not typically allowed to do with a relational database. And then finally, a key value, I'm using the term object here, is a set of key value pairs. So the difference here is that there's typically not a schema of any kind, so you don't care what keys there are. It could be any keys at all. And there's no exposed nesting. And what I mean by that is, a value can be anything you want. So you might have some kind of complex object in the value, but it's not going to be sort of visible to the system. It's just going to be a blob, a black box object that the system doesn't know anything about. Okay, so sort of only one layer of nesting is aware of the system, unlike a document store or a document object that might have multiple layers of nesting that are exposed to the system. Okay, and so his characterization of NoSQL features, admitting that there's perhaps not a formal definition of there certainly isn't a formal definition of NoSQL, but the term tends to be applied in contexts of systems that have these features. So some ability to scale simple operation throughput to many, many servers. And by simple operation here we mean key lookups or maybe even attribute lookups or reads and writes of just one or a few records, right? So these sort of needle in the haystack kind of operations, as opposed to these big analytic queries like we've been talking about with MapReduce and with databases. Okay. And second criteria is the ability to replicate and partition data over many servers here. So, break a single large data set into multiple pieces automatically. Makes you don't have to manage this yourself. And here you might see the term sharding and horizontal partitioning. The difference between the two, if there is any, is not particularly important, so you can think of them as synonyms. Whenever you see sharding, think horizontal partitioning of a database table. You'll see the term horizontal partitioning used more in the database community and sharding used more in the NoSQL community. Okay, and then a simple API, so no query language. This corresponds to the first bullet. These are the simple operations. And then critically, a weaker concurrency model than what I'm saying is ACID transactions now. Now we'll talk a bit about ACID in the next slide, but I'm not going to go into a lot of detail here. There's 40 years of research on this topic, too much to cover in this course, especially when we're mostly focused on reading data and analyzing data as opposed to concurrency control. But we will spend some time on some techniques of concurrency control in a minute. Okay. And then some efficient use of distributed. He talked about efficient use of distributed indexes and RAM for data storage. So this is kind of minimizing latency is their emphasis, as opposed to just throughput. All right. And then typically they have this ability to add new attributes to data records in various ways, as we talked about on the previous slide, right? So the lack of no schema is what you can think of here. All right, so this is no schema, no transactions, and we'll go into more detail there. No query language, but no SQL, right? And high scale. Okay. So ACID, and he talks about this term base that never quite caught on. I wouldn't typically use this term, and I'm not sure I recommend you do either. Certainly ACID is much more permanent in the vernacular than this base is. It's okay. So ACID is an acronym standing for these four concepts: atomicity, consistency, isolation, and durability. And just briefly, this is, the context here is when we're modifying records in, let's say, a database. And we can be modifying lots of different records across different tables, anything we want. And the point is, they're all lumped into one transaction. And so each one of these refers to, that's the context we're in for each one of these concepts. So atomicity means that the entire transaction either needs to succeed or it needs to fail. Right? You aren't allowed to have partial transactions succeed. Consistency is the slipperiest one in my mind, and this quote down here maybe captures that. So it's sort of any data written to the database must be valid according to all defined rules. And the question is, well, where do these defined rules come from? Sometimes they're actually integrity constraints in the database. Other times they're just sort of business logic rules, perhaps enforced by the application or just assumed by the application. And so it's a little bit difficult to say prove a system achieves application level consistency. But that's the goal. The point is, if there's only certain allowed states of the database to have, you should not have a system that allows transactions to put you into an invalid state. Okay, you should only be able to go from working state to working state. Isolation means that while the transaction is occurring, other readers and writers can't sniff partially completed values. Okay, partially you can't sniff values of data items before the transaction is complete. They only get final states, and this one is the one most often relaxed in various ways, in part because it's very expensive and also because it's not usually all that critical. And then durability just means that if you report back that the transaction succeeded, it needs to have actually succeeded, meaning it needs to be written out to some kind of non-volatile storage so that if the power goes out and the machine crashes, you don't say, hey, whoops, that transaction I accepted yesterday or committed yesterday, well, you need to do that again because it didn't take. All right, so that's not allowed. So fine. So these all make some sense with a little bit of slippery notion of consistency, as I mentioned. And then the pun here is they tried to sort of force an acronym on base, and this isn't Rick Cattell. This came from elsewhere. But the idea is, well, it's basically available. There's some notion of soft state, and it's eventually consistent. And we talked about eventual consistency, at least an overview in the previous segment. Fine. That's all I'm going to say about that. So something else I like about this paper is he sort of says, look, the major impact systems here are these three: this Memcached or Memcached, Dynamo from Amazon, and Bigtable from Google. And the reason he says these are the major impacts is you can kind of trace the lineage and show that other systems are basically taking ideas from one of these three early systems. So memcache is very, very simple, and we'll talk a little bit about one particular technique that it made popular in a minute. But it's essentially just, hey, look, let's load everything into memory, scale it out across many, many machines, right? And then we'll be able to serve read requests without having to go sort of query the database. We'll just be able to do it directly from memory. And what's also made this very, very popular is you can kind of install it on top of your either scale out or non-scale out database, and it sort of just works, right? It just makes things faster for read heavy workloads, and that was kind of a nice thing. So that's an older system, sort of on the scale of 2003, but it's still very widely used and very, very popular, and there's been all sorts of extensions to it, and so we'll talk about perhaps the most basic version. Amazon's Dynamo paper, which has been somewhat more recently released as a cloud service called DynamoDB. What they did was, they didn't invent the concept of eventual consistency, but they did sort of show that if you relax the consistency notion, that will allow you to scale way, way out. Okay, and so data fetch are not guaranteed to be up to date, but updates are guaranteed to be eventually propagated everywhere they need to be. And we gave an example of why this was a good idea in the last segment. And then Google's big table that we'll spend some time on, demonstrated that record-oriented storages could scale to thousands and thousands of machines, and that was something that databases had not shown. Okay. So let's talk about each one of these systems in turn. So memcached, as we said, is a main memory caching service, no persistence. The basic version is no replication, meaning that there's only one copy of every cached value. So if something goes down, if that goes down, then it's gone. That's okay because it's sort of a cache. It's not assumed to be the golden copy of anything. Okay. That being said, there's been many extensions that provide these various features, including membrane and membase. So this is a pretty mature system and still in wide use. And an important concept that they adopted in this context was consistent hashing. And so I want to explain a little bit about what consistent hashing is. So that's one takeaway from this lecture. Okay. So first, just for those of you without necessarily having too much of a background in programming, what is hashing? So what is regular hashing? Well, the problem we're looking at here in this hashing is a very, very general concept, very fundamental to all of programming. But in the context of what we're doing here, we're trying to assign data keys to a bunch of different servers. Okay. And the simplest way you might do this is sort of a round robin thing, right? The first key goes to the first server, the second key goes to the second server, and you keep going until you run out of servers and you start back over at the first one. And that's implemented by this modulus function. Okay, so each of these data keys is placed somewhere on one of these servers at various points. Fine, that's how hashing works. What's wrong with that? Well, what happens if I want to add more servers to the mix, right? I want to scale out I want to double the number of servers. Well, every existing data key now needs to be reevaluated. Its location needs to be reevaluated by computing k mod 2n instead of k mod n, which means every single data item is going to be remapped at once. So every time you want to add a server, you end up having to move all the data that's already in the system, and you're dead in the water. Okay. So what you want is some notion of consistent hashing, where consistent means when I place something somewhere and I add more servers, it's typically going to stay right where it is. And so there's a pretty good trick that's pretty simple to understand for doing this. Okay. So here's how it works. The first key idea is you're going to map the server IDs into the same space as the key values themselves. Okay. So we apply a function that I'm going to leave sort of unspecified and map server 1 to some point on this circle, and server 2 some point on this circle, and server 3 someplace on this circle. And now what that does is divide this space up into 3 sections. Okay. And now each key that comes around, I also map it into this circle. So this gets key 1, and this gets key 2, key 3, key 4, key 5, key 6, key 7, and so on. Okay, and now this entire region, server 2, server 3, this entire region is responsible for all of these data keys. Sorry, this server is responsible for all these data keys. And then this server is responsible for all the data keys in this region. And this server is responsible for all the data keys in this region. Okay. And so what's nice about this is now when I add a new server, server ID equals 4, well, let's say it comes around and it gets stuck right here. Well, that's a bad spot for it for my example, actually. Let's say it comes around right here. Well, you just apply the same rule. It should be responsible for every key in this region, which means that these two guys need to be moved from server 3 to server 4. Right? But you only have to move that one section of data. And so it splits at most sort of k over n data items. All right, so this is a nice trick. And there's all kinds of extensions for supporting replicas when you need to put data items in more than one place. Well, you just sort of hash it to two different places. So if you want to hash the same data item to two different places, compute h of, let's say d is the data key, and then also put it to put it in all three places, and you're done. Okay. Okay, so how do we serve requests in this setup? Well, imagine the key space is divided across various servers in the same way we described, and a request comes into the leader that may be elected among the servers, or may just be assigned top-down by the system, or could even be assigned randomly. And the naive way of doing this is, well, this server would check to see whether it has the key being requested, and if it doesn't, it would just forward the request on to the next guy. Okay, but this is no good because there could be many servers, and this would incur sort of a latency every time you want to do a read. So a better way of doing this is for each server to memorize the locations of other servers in the ring. And which servers it memorizes is like this. So it knows where itself is. It knows A plus 2, A plus 4, A plus 8, A plus 16, and so on. And what it does is it knows the key range being managed by each one of these servers. Okay. And so what it can do is forward the request to the server that is closest to the key range it's looking for. Okay. And so this takes a logarithmic number of hops away. Imagine there's lots of servers here. And keeping all this information straight when new servers come in is still, each server only has to keep track of a logarithmic number of servers as well. So everything sort of ends up being logarithmic to maintain this. Okay. Okay, so Dynamo from Amazon in 2007, which was a paper. And again, a few years later, it's been released as a cloud service called DynamoDB. Okay, and so here we're looking at, scales to thousands of nodes. You can look up things by primary index and basically nothing else. It's just a key value store, just like Memcache. Okay. Right. So what are some of the tricks it led to? Well, so some key features are that it has, so I'm talking in terms of DynamoDB, which is the implementation you can now go and use and pay for. One of the neat things here is that it offers a service level agreement on performance. And so at the 99th percentile, they promise to respond within 300 milliseconds for 99.9% of its requests. And the reason they do this on the 99th percentile as opposed to some sort of notion of the average, the mean or the medians, or the mean or the median, is that would artificially penalize the people who are using it heavily, right? They would get a disproportionate number of failed requests, right? It'd be easy to satisfy the average by only focusing on the lightweight users, for example. Okay. So Dynamo, the system, it's a distributed hash table. That's what DHT stands for. And each key is stored at, each value is stored at locations, multiple locations for replication purposes. And it's up to a replication factor of n. And so at location k, k plus 1, all the way up to k plus n minus 1. And they achieve eventual consistency through vector clocks, which I'll describe in the next couple of slides. And so reconciliation of potential conflicts when things are being read and written happens at read time, which is another maybe interesting feature of Dynamo. Okay, so writes never fail, and they cite in the paper that the reason for this is poor customer experience, right? So if you're sort of typing into your Google Doc, well, not at Amazon, if you're building an application, a web application where you say you update your status on some social networking site, and it comes back with an error message and says, sorry, couldn't commit, somebody else was editing the same, or you're editing the same status from somewhere else. Their claim is that that's more disruptive than getting the wrong read, which just seems reasonable to me. Okay. All right, and so conflict resolution for many applications, maybe the most recent write is the one that wins, or you can actually have the application control this. In some cases, you may even sort of go back and ask the user to resolve the conflict manually. Okay. Okay, so the goal with vector clocks is to detect conflicts in a concurrent read-write scenario, but not to necessarily do anything about them automatically. Okay, so in this scheme, every data item is associated with a list of server timestamp pairs that indicates its version history. And so in this example, some value D was read by a client, and D1 was written back at the server called SX. And so what SX does is append this fact to this vector clock. So at timestamp 1, server SX created a change. Then some other client reads D1 and writes back D2, and you might want to append to the vector clock both values, but this change descends from D2 descends from D1. It was handled by the same server, and so you can garbage collect this part of the vector clock, right? So it's the same server with a higher timestamp, means that the old version with the older timestamp is not needed anymore. Okay, and since there were no other conflicts to work on. Okay, but now independently, two different clients read D2 and write back different values. One writes back D4, one writes back D3, and these two requests were handled by different servers, SY and SZ. And so these facts get recorded in the vector clock since they're different. Now, the context here we call this sort of vector clock the context. The context will reflect this fact when the next read comes in. It'll see that, oh wait, there's a conflict here because we have the same timestamp but two different servers. And you can either ask the client what to do, or you apply some heuristic where the later one runs. These may not be timestamps like integers. They could be sort of actual clock timestamps, in which case you make an arbitrary decision and just pick it and go. Okay. So that's how vector clocks work. So in the example, just to sort of run through what we just saw, a client writes D1 to server SX and creates this value. Another client reads D1 and writes back D2, also handled by SX, and D1 was garbage collected. Then separate clients read D2 and write back D3 and D4 on two different servers, SY and SZ. And then another client reads D3 and D4 and notices it and finds that there's a conflict. The system reports that there's a conflict to be handled. Okay, so let's practice with these. Here's two different vector clocks, and you figure out whether there's whether they represent a conflict or not. So in this case, we have server SX with a timestamp of 3, and on this data item, server SX with a timestamp of 3, and then each one is a different server with different timestamps. So is there a conflict? Well, yeah, there is, because on one version path, SY made a series of changes, and on another version path, SZ made a series of changes, and they didn't talk to each other because they don't reflect each other's changes. So yes, there is. And on this one, it's at the same server at a later timestamp. So is there a conflict here? Well, no, because they weren't handled by different servers. So really just this one subsumes that one, and we're okay. So on this one, we have server SX with 3, server XX with 3, server SY with 6, server SY with 6, so they agree so far. And then this one is an extra change of server SZ with a timestamp of 2. And so no, there's no conflict here because they agree wherever there's this is just an extra change on top of this one. So this guy wins. Okay. Then this next one, server SX with a timestamp of 3, server SX with a timestamp of 3, server SY with a timestamp of 10, and this has server SY with a timestamp of 6, and then some later change at SZ. So is there a conflict here? Well, there is, because this one is later in time on SY, right, 10, than this one is. But then, and if that was all there was, if it wasn't for this guy, if it wasn't for this guy here, well, that'd be okay. We would just pick this one because it's later. But because this one's here, we now have some changes at SZ and some changes at SY that were both forward in time from the latest point that they agreed on. And so we don't know how to resolve that. And so yes, there is a conflict. And then similarly here, SX and timestamp 3 and SX and timestamp 3. Well, here we have SY and SY10 is the same as the last one, but here instead of 6, it's 20. And so it's later than this 10. And then further we have a change at SZ. And so is there a conflict here? Well, no, because this one is strictly later than that one is. On all the servers that they share, it has later timestamps. So it strictly subsumes it. And so no, there is no conflict. Okay. So those are, in the last time we talked about consistent hashing, in this segment we talked about vector clocks. These are two little gadgets to be familiar with because they come up time and again in these NoSQL systems and in other systems in general. Okay. All right, so Dynamo also talks about a way to parameterize the level of consistency. And this comes up occasionally in papers, so I just want to make sure you're exposed to it. So the idea here is that you have two parameters, R and W, and R is the minimum number of nodes that need to participate in a successful read. Okay. And W is the minimum number of nodes that need to participate in a successful write. So this is sort of how many replicas you write to and how many replicas need to respond from a pool to know that you sort of have all the information. Right? Because if everybody's updating everything all the time, it might be that you have 20 different servers. They all have a different version of the data item you're trying to read. And so the question is, how many of these do you need to sample before you feel like you have the right one? And so for a replication factor of n, if R plus W is greater than n, then you can claim consistency. But often you want to set R plus W less than n in order to achieve lower latency. So you don't want to have to actually contact too many servers in order to satisfy some read request or write request. Okay. So if you see that notation, this is what it means, but I'm not going to describe too much more about it because I think the sort of the formalism falls over a little bit under a little bit of scrutiny, but that's what they're talking about when you see this discussion on, say, blog posts. Okay. Okay, so the next system I want to look at is CouchDB, which began in 2005, but is undergone a lot of updates and is still pretty popular today. And so this is an example of one of these document-oriented stores that Rick Cattell talked about. And so here, just to look at the features we're talking about here, we've got the scale, we've got primary index. Now we start to see the requirement for secondary indexes, meaning that you can look up not just by the key, but by other kinds of values in the document, and we'll see how that works. Okay, and then transactions also are a little bit better. We can what I mean by record here is that you can change multiple values within a single document object, which is a set of key value pairs, as opposed to just a single key value pair. Okay. And then there actually is some support for analytics, and we'll see how this works too. This is all through this concept of views in CouchDB, but you can actually run little MapReduce scripts to compute, derive new values from existing document source. All right, and then the other notion we have here is views, which is somewhat unique. You can see this column is fairly sparsely populated, and I hit the concept of views pretty hard when we're talking about relational databases, and argued that it was pretty fundamental to not only the relational model, but a pretty important concept in general. It gave you this notion of logical data independence. And so whenever you see views, that's a good thing. And so CouchDB has them as well. All right. So the data model here is document oriented, as we said, where a document is a set of key value pairs. And so here in this application, these are perhaps blog posts where they have a subject, the key is subject and the value is some text string, and they have an author, and they have a date on which they're posted, and then they have a set of tags, and this is sort of what makes it a document model. We said they could be sort of nested, so this is okay to have a list of objects here. And then they have a body, which is another string. Fine, and you'll notice that this is actually JSON compliant. We looked at JSON in the Twitter assignment, and so it's another occurrence of this. And one of the reasons why I wanted to make sure you're working with JSON before is it does get popular. And so CouchDB, all data is represented in JSON, and all the requests coming back are all represented in JSON as well. Okay. So how do updates work in this context? Well, as we mentioned, they are, you can make it is fully transactional within a single document. So full consistency within a document, meaning that I can sort of grab hold of the document and logically sort of lock it and make it whatever updates I want. Now, it doesn't actually take a lock, because it uses what's called optimistic concurrency control, meaning that it sort of assumes that conflicts aren't going to happen optimistically. And so now if I check out that document and try to make updates to it anywhere I want all throughout it, and then try to commit that change, and someone else is doing the same, has committed their own changes in the meantime, my changes will fail. But we assume that doesn't happen that often, so it's okay to just sort of fail in those cases. And really what all you have to do in that case is check out the new changes and make whatever changes you want. Fine. But there's no multi-row transaction. What I mean by multi-row here is multi-document, right? So you can't say, for example, when I update my status, I have to update my document that describes my current state of the world. But maybe I also want to update all my friends' walls, right? Their pages that reflects my new status. And you can't guarantee that happens synchronously in CouchDB. But, in this particular application and in many others, maybe that's okay. All right. You can do it in two separate steps. You update your status and then you update theirs, and there'll be a period of time when their, view of your current status is out of date, but maybe that's all right. Fine. All right, so this notion of views works like this. A view specification, which is itself a CouchDB document, a set of key value pairs, but it's sort of a special one, looks like this. There's some metadata information here, and then there's this key views, which is a dictionary of things. And so this specification has 3 views in it: one called all, one called by last name, and one called total purchases. And each one of these views is implementing a set of key value pairs. Right? It's going to be implementing a dictionary. And so the all view, okay, and so fine. So how are these implemented? Well, speaking of recurring concepts, views are recurring from logical data independence in relational databases. And here MapReduce is recurring, even outside the context of literally Hadoop. Okay. And so here the map function, reduce function are actually written in JavaScript. Again, everything in CouchDB is JavaScript. And they look like this. So the all view has just a map function, no reduce function. And in JavaScript, you can write these anonymous functions like in this sort of syntax. So this function doesn't have a name. It just says, hey, I've got a function with no name with a single argument called doc. And the body looks like this. It says, if doc.type equals customer, then emit a key value pair where the key is null and the value is doc. So we don't really care about the key in this case. We just care about the doc. All right, so this is all customers. Fine. The by last name view you can imagine the key is going to be last name in this case. And so here we have another anonymous function. If doc type equals customer, then emit the last name followed by the entire document. And so now this allows clients to search efficiently by last name. And these views are in CouchDB are computed, they're materialized sort of eagerly and stored in these distributed B-tree structure or index structures to support various lookups. And so this is how they implement those secondary indexes in that column in our table. Okay, so now we can look up by last name as well as by document ID. And so you can even go a little further. You don't have to just do simple key value pairs. You can even do a little bit of computation. So total purchases here, the map function again takes in a document and says, well, if doc type equals purchase, so I'm not talking about customers anymore, just purchases, then emit the key of doc.customer and the value of doc amount. But then we're also going to define a reduce function, and the reduce function adds up all the values of the amounts. And so here we have, given a customer, if I give you a customer, you can return it's the total amount of all of its purchases. Okay, and CouchDB maintains all these views as things change with eventual consistency sort of semantics. And so we have a lot of things going on here with one concept. We have secondary indexes, we have logical data independence, we have map reduce computation. Okay, so I had checked the box in the table saying that CouchDB could do joins and analytics, and it's not really quite true. They're somewhat limited. So let me show you an example of how they do sort of joins. They have this concept of view collation, and what you can do here is write a map function in a view that looks like this. And so here we're trying to group together all the comments associated with a post. So it's sort of a join between the comments table, if you will, and the posts and the blog posts table. And so this map function is the same kind of thing we did in the MapReduce assignment to do a join. This is what you have to do when you do a join in MapReduce, is you pretend like the whole collection of documents, regardless of type, regardless of source relation, is one big set of objects. And then in your map function, you sort out which one's which and make sure to hash it on the same key. So here, the ID of the document post, and then in this document, doc.post refers to some post ID. And so now, post ID equal to 1 and all the comments associated with post ID equals 1 will go together. But they do this funny thing. They say the key here in the key value pair is document ID followed by the number 0 in the one case and the number 1 in the other case. And what's happening here is that everything in CouchDB is sorted. And so you've got things sorted by document ID and then sorted by this extra bit. And so now you have the post ID coming first and then all the comments coming second. And now what you could, you'd think that you could just do a reduce function to actually compute the join that you might want, but it turns out reduce functions don't quite work that way, and there's some scalability issues. So what people recommend is to do this view collation trick where you still spit out the data in sorted order, but then you can query it. Say a client application could query it like this, where they say start key is just the post ID without the extra prefix at all, and the end key is post ID with the number 2. And so now this gets the full range of the post ID which has the key of 0, followed by all the comments with a post ID of 1. So you got everything in one big list. And now you could process it in order to show it, show it in the application. So you essentially constructed the join by cheating with the order. Okay. So fine. So perhaps you could argue that you have some joins in analytics, but it's a big glib to say so. Okay, so the third influential system that Rick mentioned in the paper is Bigtable from Google, which is a paper from 2006. And so here we're looking at primary index lookup, secondary index lookup. Transactions are also at the sort of scale of an individual record. Joins analytics is not supported by Bigtable directly, but in the in HBase, which is the open source implementation of it, and in Google's implementation as well, it was sort of designed to be compatible with MapReduce. And so you can run MapReduce over here over the same data that's stored in big table, so they're sort of complementary. And then there's some notion of integrity constraints or schema here, and we'll talk a little bit about how that's implemented. There's no views that I can see, and there's no sort of language level or algebra level for manipulating these things. They're all sort of NoSQL style micro interactions with individual records and cells. Okay. So this is a paper in OSDI from 2006 and some overlap with the authors of the MapReduce paper, and it was sort of designed from the start to be complementary of MapReduce. So if you can remember, what was one of the main things that was missing from MapReduce, or maybe a few things that were missing? Well, in particular, you couldn't look things up by index. You couldn't get these little sort of low latency accesses. And so, for example, if you wanted to find all the records, given a big data set, you want to find all the records in some other data set that correspond to it. You want to do some sort of a join. The best you could do is process. You had to touch every single record. There was no way to zoom in to just the right ones you wanted. Okay, and so Big Table provides that fast key-based lookup, but you can still process the overall data as a big set of key value records with MapReduce. Fine. So the data model here is a sparse, distributed, persistent, multidimensional sorted map. And what they mean here is that you can basically access any cell in a big table by giving a row ID, a column name, and a timestamp. Timestamp isn't really described in this English description here. It's for versioning. So when after you have updates, you'll keep track of past versions of the same cell. Okay, and so if you provide these three parameters, Bigtable will return you a string quickly. All right. So each row is data is all sorted lexicographically by the row key, which is this row ID in this bit, right? So this is some sort of primary key in sort of relational language, or just a key in kind of a NoSQL framework. And then this key range, I say that they're integers, then contiguous subranges of this set of keys will be assigned to a tablet, right? Okay, so this is a little different way of dividing up the data than we've seen in the past in at least one system. We talked about a parallel database model, and we happen to use the example from Teradata. And so how did they break up data? Well, they did it by hashing, right? So every individual record would be sent to a server according to a hash function, which you can generally just think of as sort of round robin. The point is that two keys that are next to each other in space, so sort of timestamp 5 p.m. and timestamp 5:01, there's no reason to believe that 5 o'clock and 5:01 are going to be on the same server in Teradata's model. Here they are. So what are the pros and cons with this? Well, if you're going to typically access a whole range of keys at once, it's pretty nice to be able to, when you get one, you get the others too, sort of for free, because you're pulling them all back. However, if one particular key range is much more popular than the others, just by using the time example again, the most recent data perhaps is the most popular. And so if all the requests are going to that one key range, then you've got a bunch of idle servers hosting all the other tablets that are corresponding to older times, and all the requests are going to this one tablet. And so for that reason, Teradata sort of chooses to hash everything, so that on every request, all the servers may have to be accessed, but that's good for scalability. Okay. So pros and cons. All right, so the tablet here is the unit of distribution and load balancing. So they'll move tablets between servers as things start to get unbalanced, right? If your key range is, January, February, March, April, May, and there's a whole lot of data coming in for March, they'll split that into multiple tablets and start moving those tablets around between servers in order to balance things. Okay. So within a single table, you can have these groups of columns called column families, and the column names have the family right in there as a qualifier. And this family is the basic unit of access control, so you can provide permissions on a group of columns. Memory accounting, in that they're sort of allocated as a unit in memory, and then disk accounting, so they're moved around on disk as a unit as well. Okay, and so they make this point that typically all columns in a family are the same type, which I find a little unusual because they sort of talk about it being the basic unit of access control, which suggests that there's, things that go together for access control, sort of social security number and employee ID or something, may or may not be the same type. So there's sort of a logical grouping requirement that they seem to be trying to meet, but then they're the same type. They have to be the same type, which is for a very technical reason, specifically because they want to compress these things. So if you have a whole bunch of integers, it's easier to compress than if you have a mix of integers and strings. Okay, so I think they're trying to kill too many birds with one stone here. All right, and then each cell can be versioned, which is the third part of that key lookup, right? Row ID, column name, and timestamp. And each new version increments that timestamp. And so here you can enact different kinds of policies where you only keep the latest in versions, or you keep only the versions since a given timestamp. Fine. So how these tablets are managed is a master will assign the tablets to tablet servers, and the tablet server handles reads and writes from the tablets it controls. Okay, and so clients communicate directly with the tablet server as opposed to having to go through the master every time, which helps with scalability. Okay, and then when a tablet starts to get too big, it'll split it and load balance it. All right. So the metadata keeping track of where tablets are located is organized itself in another tablet. So there's a root tablet here that describes each record in here describes a group of records, a group of location records in a bigger table. And then each one of these metadata tablets gives the location of a particular user table. Okay. And so this is how you sort of keep track hierarchically of where everything is at one time. And so Chubby that they mention in the paper is a distributed lock service for controlling access to these things. I'm not going to talk too much about it. Okay, so how are reads and writes handled in this system? Well, there's a table in memory that stores a sequence of updates as they occur. Okay, and a write operation adds a record into the memory resident table, but it's also written to a log for fault tolerance purposes. Okay, so if this server goes down, it reads the tablet log and can reconstruct what's going on. And then read operations are served by reading these SS table files, the actual data itself, but then also by applying the updates from the mem table on the fly. Right? So it needs a stream. It says here's the value, and then here's the stream of updates I need to apply to the value to get the true value. Okay, and then there's two. So this is fine, but what happens when the mem table gets bigger and bigger and bigger? Well, there's two types of events that occur to do the bookkeeping here. So one is a minor compaction, and this is when the mem table gets big, it gets written out into a new SS table file, and the changes are merged. Okay, and then a major compaction is take all the SS tables and rewrite them all into one big one that may be split into multiple files, and also clean up any deletes that have occurred. So deletes are just appended as instructions, but it doesn't actually remove anything, so they're sort of garbage collected. Okay, and so this way you can keep sort of the read throughput pretty high and sort of keep this upkeep going on in the background. All right, so there's a host of other tricks here too, where they can do various forms of compression specified by which can be specified by the clients. There's some different ways of doing it. They use Bloom filters to speed up existence tests. So if I give you a row ID, a column ID, and a timestamp, and say find me this value, what these Bloom filters allow you to do is to very quickly determine whether that does not exist in the system. So these Bloom filter data structures are pretty cool, and I'm going to walk through them in this course in a couple of weeks. Okay, so they help you quickly determine whether that key does not exist in the system and avoids disk accesses during reads. All right, and then there's locality groups you can define, which is another layer of organization on top of families, and these are groups of column families that tend to be accessed together. Fine. And then another trick here is to make sure that the SS tables, these disk chunks, are actually immutable. They never get written directly. The only time they get written is when these major compactions happen and the whole thing is sort of reorganized. And so that means that the only writable data structure is this mem table. And so the amount of concurrency control to keep things down, it remains pretty simple. Okay. Okay, so Google Bigtable, again, had a lot of influence, and one of the major outcomes is, just like MapReduce, it was taken up and implemented as an open source project called HBase. And so where Bigtable was compatible with MapReduce, HBase was compatible with Hadoop. And in one slide, there's not much difference here, but I just want to mention the terminology so you've seen it. That there's table at the top level, and then region, store, and then mem store and store file. And so the exact names of these structures are a little bit different, and they did insert one more layer of abstraction, which is this region. Fine. And then how this sort of is compatible with MapReduce is that, you know, each one of your map functions will process a single tablet, and so it's sort of one-to-one with the blocks of data that we talked about when we talked about MapReduce. And then I just sort of ask this question, sort of open-ended, is that there's this notion of speculative execution in MapReduce that we talked about, whereby for fault tolerance reasons, it might kick off the same map task twice on two different replicas of the data. And the reason for this is that if one fails, well, you have the other one, right? So you don't have to start over from scratch. But you know, in this environment where you're now working on data that is being actively updated, and that's what HBase and Bigtable are designed to support, is updates, it's not quite as clear to me what's going to happen when you have, you know, it's possible, because of eventual consistency, that these two tablets will not always agree instantly. On the same record, they'll agree, but different records within the tablet may not. Okay, and so just an example of when you sort of mix these two systems and there are no sort of system-wide transactional guarantees or system-wide even properties, that you can run into trouble. And I think that a general theme here with these sort of NoSQL systems, including the ones implemented, you know, designed by Google, is that you're kind of offloading some of this responsibility to the application, to the programmer, to sort of sort this out and make sure it's okay. Okay, and we're going to come back to that in just a couple of minutes. All right. So after Bigtable, several years later, there's a paper by a bunch of folks at Google about a system called Megastore that I'm not going to spend a lot of time on, but it's basically, you know, they found this point I sort of just made, is that these loose consistency models can complicate application programming. And what they wanted to do is provide a little more system support for certain kinds of safe updates. Okay, so here, instead of full transactions being safe within an individual record, as they are in Bigtable, they've extended it with this notion of entity groups. And so an entity group, this should be on this slide, and an entity group is a set of records that tend to go together, tend to be accessed together. Okay. So maybe, again, this is the blog and all of its comments, for example. You know, each one of these is a record, because it's an extensible record store, so it's okay for them to have different schemas. But they all tend to go together. Okay, and so what they've done is extend transaction support over an entire entity group, you know, a set of related records. Okay, so they still get the scalability by not requiring full system-wide global, you know, synchrony, but they allow you to sort of, they get away from this problem of, you know, very frequently I might need to update one record and then update all of its sort of children records at the same time, and I can't do that in any kind of safe way. Okay, so fine. Fast forward one more year, and so there's a 2012 paper on a system called Spanner, and I just want to mention these quotes, and then we'll talk a little bit about the system. And this one is still sort of being explored by the community. it's not available actually for use, but the paper is being explored and the idea is being explored. So, for example, you don't see an open source. Actually, yeah, that's not true. You do see there has been a couple open source implementations of the ideas in Spanner, but they're not quite as popular as some of the open source implementations of the other Google systems. Okay, so it says even though many projects happily use Bigtable, we've also consistently received complaints from users of Bigtable. It can be difficult to use for some kinds of applications. Those that have complex evolving schemas, or those that want strong consistency in the presence of wide area replication. Okay. And so then they go on to say, we believe it is better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions. And so this, the database community could have said, well, sure, well, duh, right? That's exactly the point, is that system-supplied support for transactions is always a win, right? Because it's difficult, error-prone, and expensive to try to do this at the application level. And more importantly, it's fundamentally wrong in some sense to do it at the application level because the application doesn't have global knowledge of what's going on, right? Only the system does. So fine. So although Spanner is scalable in the number of nodes, the final quote here, the node local data structures have relatively poor performance on complex SQL queries because they were designed for simple key value accesses. And then mentioned algorithms and data structures from the database literature could improve single node performance a great deal. Again, it's somewhat of a Google style approach to the problem of reboot everything, rebuild it all from scratch, and then sort of cherry pick and bring things in. So this has been working pretty well, and they have fantastic impact in the community. But there's a lot out there in the database literature and in database systems that could have been used from the start. I mean, in fact, trying to start from the beginning and just say we're going to build a big Google-style parallel database may have been a good choice, rather than sort of getting completely away from it and then coming back incrementally and finding yourself in a SQL system. Now, I sort of skipped over what Spanner is. It's planet-scale database system. There is a SQL-like language. Well, actually, let's go back to our. I know what I'm missing. I'm missing our table here. Let me flip back a few. So here it is down here. So I'm missing a slide here where I showed it. So really big scale, primary accesses you can access by other attributes. There are transactions, and in fact they're global this time. They're real ACID transactions. It's not clear to me whether joins are supported. I suspect they are because they keep talking about SQL, but I couldn't find an example of whether it is or not. There is some notion of schema, and they do sort of protect against data that doesn't conform to the schema. There is some notion of logical data independence, although they don't talk about it much. There is a SQL-like declarative language on top of it. I didn't see much evidence that they're doing a whole lot of fancy optimization, and I did just show you that quote of where they say that their performance is sort of poor on complex analytic queries. But that's something that probably could come along somewhat quickly. Okay. So fine. So that's Spanner at a high level. Let me give you a couple more details about what the system does. So the data model here is this notion of directories. And these are a set of contiguous keys with a shared prefix. So you can think of it kind of like a tablet was in Bigtable, but now they have this notion of multiple logical tables being sort of interleaved. And so if you're not used to staring at the syntax, don't worry too much. But those of you who are thinking in terms of DDL in a relational database, they have kind of a create table language that looks like this. You create table users with 2 columns, and then you give it this keyword directory. And then you have a create table albums with some columns, and you have this keyword interleave in parent users. And what you end up with is something like this, where there's a user with all of its albums and a user with all of its albums. And so you can see here that what we've been talking about, all these different systems are experimenting with ways of getting these nested data structures, hierarchical data structures, that look a lot like what we saw way back in the 60s, right? And the motivation is the same as it was then. It's actually really, really fast. When you're going to access, when you want to pull up a user and then immediately pull up all of its albums, it's really fast to access this way, right? But I'd probably speculate that the reasons why the relational approach eventually replaced these, it can and will happen here as well, is that performance is not the number one priority a lot of time. It's minimizing the amount of developer headaches. Okay. So remains to be seen, but I think that this incremental walk step towards a big new scalable relational database is underway. Now again, that doesn't mean that I'm saying use all the old databases. They really were designed for sort of a different workload, and they really don't. There really is no evidence that they scale to some of these levels. But that doesn't mean that you sort of throw out all the everything we learned. Okay. But that's more me editorializing. So fine. So how this works is there's a universe master at the very, very top, and this is just a singleton. There's only one of these for deployments, and they sort of imagine there might be only one or two of these deployments anywhere. So they have sort of one for test, one for production/test, and one for production, and that's it. So many different applications will all use the same deployment of Spanner. And so this is mostly just status information about the zones. It doesn't interact with clients at all. And then there's a placement driver that's responsible for moving these directory sets of records around for load balancing purposes, and this happens on the scale of every few minutes. All right. And then within a zone, there's a zone master that assigns data to span servers. And there's a location proxy that sort of knows where everything is and routes requests to the appropriate span server. And then the span servers themselves serve data. And so in here, it's starting to look a little bit more like Bigtable. Zone is essentially an individual Bigtable deployment. Okay. So inside of a span server, this is where the big difference here is this is where they're going to try to support fully consistent transactions. So across these, within a group of these replicas, they support two-phase commit. This only is needed when a transaction actually accesses data that's across, that is not contained in one particular replica. Okay. Other than that, it just skips over this logic, and it doesn't cost anything. Okay. And then one step down below this across. So this is, sorry, I guess I'm using the wrong terminology. So two-phase commit is across groups, and when the transaction only is contained in one single group, then you drop down a level and you run the Paxos algorithm that I didn't talk about in detail, but I mentioned exists, in order to sort out the reads and writes for, in order to handle the write. Okay. And the only other piece I'll mention here is that this term Colossus is new. It's the successor to Google File System, and Google File System is the original term for the open source implementation of HDFS, which underlies MapReduce and Hadoop. Sorry. GFS is to MapReduce as HDFS is to Hadoop. So when I'm throwing these acronyms at you, that's how to keep it straight. Okay. So that's all I want to say about Spanner in particular. But just take a step back and look at all the different systems that Google has for a second. MapReduce was a paper in 2004 that had a ton of impact. Bigtable had a ton of impact, and then later there's Megastore. There's the system Tenzing that we didn't talk about, but it's a SQL system on top of MapReduce, much like Hive, if you were familiar with that, or if you remember me mentioning it. And then Spanner very recently. And so you can sort of organize these things into a timeline this way, just to kind of get a sense of this. And because these systems have had so much influence, I want you to be aware of what they are and sort of how they fit together, so it doesn't just sound like a big jumble of terms. So MapReduce was, one of the earliest ones. It wasn't quite the earliest. There was actually another one called Sawzall that didn't really get a ton of traction, but it was a nice paper. And then Bigtable came a couple years later, and I drew a dotted line there representing that they're sort of compatible or designed to go together. One was for MapReduce for analytics. Bigtable was for the sort of micro operations. And then both of these had, a few years later, had an open source implementation in Hadoop and HBase respectively. Okay. Fast forward a few more years, and you've got Megastore and Spanner coming very quickly, one right after the other. And this heavy blue line represents, it's pretty clear that the influence is fairly direct. In fact, I would suspect that there's a lot of code being borrowed. I mean, Megastore makes plenty of references to Bigtable, and Spanner makes references to both Megastore and Bigtable. And the papers have many of the same co-authors. Okay. And then MapReduce depends directly on, Tenzing depends directly on MapReduce. It provides a SQL layer on top of MapReduce. And then there's some other systems here. One is called Dremel, which was originally for very fast aggregate queries, but really just aggregate queries, but at extremely low latency. So this is, in the analytics camp, because you're doing these sort of aggregate questions as opposed to sort of micro updates. But it was extremely low latency, unlike MapReduce, which is more of a batch system. And so this is a great fit, and it's a very nice system. And in fact, since then they can do joins, not just aggregates. And more importantly, this was exposed as a service that you can just use directly over the web, even in your browser, called BigQuery. And that's an important one to watch. It's one of the few systems that is available as a service through as a cloud service, but scales to very, very large data and supports analytics. Okay. And then another one that we won't talk about yet, but we will come back to, is Praegle. And this adds the one secret ingredient that is sort of near and dear to my heart, which is iteration. And what I mean by that is when you run MapReduce jobs to do analytics, you're sort of taking step 1 and then step 2 and then step 3 and you stop. But for many kinds of tasks, especially in data science, many of these analytics tasks, these machine learning tasks, you have to do something again and again and again and again until some kind of convergence condition is reached. And Praegle and one of our systems and a few other systems are the ones that tried to notices this limitation of MapReduce and extend it. So people were doing this with MapReduce, but they do it sort of in fairly ad hoc ways. Okay, and so we'll come back to that and talk about it. But, analytics, low latency, micro updates. So there's two big classes of systems, and then analytics with iteration is perhaps a third class of system that we'll talk about. Okay, so going back to the grid, we can highlight those systems that were based on MapReduce itself. The MapReduce paper itself in 2004, and these language layers on top, Pig and Hive in 2008, where Hive is SQL and Pig is a relational algebra looking language that we'll talk about in some detail in the next few segments, and Tenzing, which is also SQL, and Impala, which is also SQL, where Tenzing is from Google and Impala is from a company called Cloudera that's a pretty eager evangelist of MapReduce and Hadoop based technologies in general. Okay, so one trend I think you see is that these declarative languages on top of the parallel processing primitive of MapReduce are really here to stay, right? So people that were relatively against these kind of languages are certainly doing it. Now, it's also fair to say that the enterprises in general have made a pretty significant investment in SQL expertise. So even if they're attracted to the advantages that Hadoop might bring, they're pretty much demanding SQL. So this may be a response to this inertia from having invested in SQL in the past. I think that's certainly true. However, it's also true that the desire for a declarative language is reasonably well founded for reasons that we've already talked about. Okay. So you can put these systems on this timeline, and the only point I want to make about this is that there's a bit of a gap between the paper in 2004 and these systems in 2008. But then as soon as you had Hadoop, the system itself, developed at Yahoo and released as an Apache open source project, you sort of immediately see an ecosystem start to emerge of extensions to it that add these, in particular adding these languages on top. And so I think that the need for a high-level interface is motivated by how quickly they came around as soon as Hadoop was out. And again, it didn't stop with these later systems a few years later. Okay. And actually, not on this page, there's potentially hundreds of, if you include, research projects based on extensions to MapReduce, there are really, really a lot. Okay. And so this is some of the most popular ones. All right. So another subset of this grid that you can look at is just the NoSQL systems. Now, the whole last few segments have ostensibly been about NoSQL, but I've also included these kind of analytic systems in here, MapReduce-based systems and a few others, for example, Dremel and Spark and Shark. Dremel is a system from Google that is the back end of a query as a service system called Google BigQuery, which is pretty nice. I recommend taking a look at it. You can sort of upload data and put it in there, and it doesn't matter how big it is, and you can kind of query it at very low latency speed. Spark and Shark come from the AMP lab at Berkeley and are part of the Berkeley Data Analytics Stack, BDAS or BADAS. And Spark is a language level on top of, it's not MapReduce, but on top of a parallel processing system. And Shark is an SQL layer even on top of that. Okay. And so a couple of the distinguishing features of Spark is it loads everything into memory, processes everything there when possible, writing things out to disk only for fault tolerance reasons, so much less often than MapReduce. And it also supports iterative processing, which is pretty important, and we're going to come back to that a little later in the course. And then Shark again is just SQL on top of this. All right. So within these NoSQL systems, one thing you can look at, there's not much I want to say about this diagram, except that, to point out that there's been this sort of the Cambrian explosion. So first you had sort of memcache, which is again just a caching layer for really the real system, and the real system was a bunch of MySQL databases that weren't really working all that well for the requirements they're having them used for. But you could bring things into memory and keep it there, looking it up by name, and it was just sort of a performance enhancement, a free performance enhancement if you invested in this system. The real approach of throwing out everything you have and replacing it with a NoSQL system came a little later. And so the only couple points I want to make is that there's been kind of a Cambrian explosion of different systems around this time, and that this space in here is not nowhere near as empty as it looks. I've picked out a few systems here, but really the emergence of new systems in the space hasn't really slowed down much at all. So really filling out the design space here since around 2006. And the only other point I make is that these quite popular document-oriented data models systems, CouchDB and MongoDB, have actually been around for quite a while. So they've been, the original release are 2005 and 2007. So sometimes I think they seem like newer systems, but they have some maturity. Okay. So then finally, one other point I want to make is about this column that I've called joins and analytics. And so one of the distinguishing features of NoSQL systems is that they typically don't support any notion of joins, and many of the proponents of these systems would argue that that's okay, that the joins aren't really necessary. So the argument about why you can get away from joins goes something like this. When you're joining two tables, you sort of have one record and then a bunch of corresponding records in another table. Well, if I put all those corresponding records and co-locate them with the parent record, right, then I can access everything all at once, and I don't actually need to compute the join. Okay. So that works, and it should sound somewhat sort of familiar because it was part of these network and hierarchical data models that we talked about in the discussion of how we motivated relational databases. And if you remember that the downside of this was that you had kind of one dominant access path into the data, but any other access path was either not supported at all or was inefficient. Okay. And if you wanted to reorganize your data to support a different access path, or because your needs changed, well, a lot of your code might have broken and you would need to sort of rewrite it. Okay. And so this tension between buying yourself a little bit of performance by organizing the data in a pretty rigid way versus the development time that you save by not having to rewrite your code whenever you want to reorganize the data, that equation sort of balanced a certain way in the early 70s, and I would claim that it still balances the same way now. Now, this is not to say that commercial databases, relational databases as they stand today, are necessarily meeting everybody's needs. I think they're clearly not for a variety of reasons. But to sort of throw out what we know and give up on this flexibility that was earned from the relational data model in favor of kind of upfront decisions about one dominant way of organizing the data, I'm not sure that's the right one either. So that's one point I want to make. Another point is that there's not necessarily one right way of decomposing things or one right way of even evaluating a join, even if you support them. Okay, and this is a point I've made before, but I want to bring it up again in the context of NoSQL. So in a pretty classical web application scenario, if you want to show all comments by a user named Sue associated with any blog post by a user named Jim, there's a couple different ways you could do this. You could look up all blog posts associated with Jim and then fetch all corresponding comments, filtering for Sue. Or you could go the other way. You could find all comments by Sue, and then for each of those comments, look up all the blog posts by Jim. And either one of these ways may or may not be available to you if you've already organized your data a particular way. But even if they are available to you, it's not clear which one's the right one. And there may even be a third method that sounds a little wild, but it's filter all comments by Sue and then independently filter all posts for Jim, sort them by some sort of blog ID, and then pull one from each list and walk over the data that way. So that sounds a little wacky, but that's just a sort merge join that you may or may not be familiar with. And if you're not, that's okay. But the point is, all three of these are perfectly valid, and the right one depends on the details of the data that you as a programmer, as an application programmer, may or may not have access to, and that may change from time to time. And so really only the system is equipped to make this decision. And so being, sort of succumbing to the tyranny of the initial design decision at the time the database was built or designed is one problem. Another problem is that even if you have some flexibility, leaving it up to the programmer to make the choice over the right way to access the data is asking them to make a decision for which they aren't equipped to make. Okay, and so this is something that does not happen with relational databases. Neither one of these problems exists in the same way. Okay, so I think trying to inject some of that smarts back into these NoSQL systems is a good idea, and we see that trend happening. Okay, so that's maybe the takeaway that I want you to have. Okay, so that's all I want to say about this grid, but let me give you a little bit of a character of a response to NoSQL by Mike Stonebreaker in Communications of the ACM. And there's a couple of different blog posts here that talked about two different arguments in favor of NoSQL, and they responded to each one of those arguments. And so I'm mostly going to focus on the second one. So those two pro NoSQL arguments are these, where he sort of points out that there's two value propositions offered by the NoSQL community. One is performance, and the story, as Mike says, that I more or less agree with, is that these people started out with a MySQL deployment of some kind, and they had a hard time scaling it out in a distributed environment. And then they had two choices. Either they could invest in a large-scale relational database and pay corresponding license fees, or they could do something different, use one of these NoSQL systems. All right. And then the flexibility argument is like, well, look, my data doesn't conform to a rigid schema. So in the performance argument, I'm not going to spend too much time on this because we talked about the trade-offs associated with different choices in transactional guarantees in these various systems. And the other part of the argument that Mike makes has more to do with database internals that we didn't necessarily cover. So let me focus on the flexibility argument. So an observation that he makes that I think I probably agree with is that, who are the customers of these NoSQL systems? And so it's a lot of startups and a lot of web startups. And it's not quite such the same penetration in the enterprise, okay? At least not yet. So why is this? Well, one argument is that most of the applications in the enterprise are traditional OLTP. And if you don't know what OLTP means, online transaction processing. And so these are sort of, bank records, right? Things where getting the transactions right really matters. Okay, and it's OLTP on structured, organized data. And so there's a few other applications around the edges, but they're perhaps considered less important, right? It's okay to take a high-risk system because the application itself is of less interest to, executives. Okay. And so really no ACID compliance, no transactions is equivalent to not much interest in the system. It's not okay to screw up mission-critical data. But for that for some other application around the edge, maybe it's okay to experiment with a NoSQL system. Okay, and then second point he makes is that relying on these low-level query interfaces is a real tough sell. And he calls up Codacil, which is an early data manipulation language that predated the declarative languages that we've been talking about. But we've sort of been down that road, and it's tough, and it's why these higher-level languages were invented. And again, we see it with MapReduce, which is admittedly analytics as opposed to pure NoSQL, but we see that the value of these higher-level interfaces pays off. Okay, and then the third point he makes is that NoSQL means all bets are off, right? There's no sort of homogeneity at all between all these different deployments. And so if in a typical enterprise you have, maybe 10,000 databases, you already have enough of a trouble trying to integrate data from these databases because of the heterogeneity within their schemas. But at least you know that you're always working with rows and columns, and at least you have kind of a standard interface to manipulating them. Okay, and so having the number of design decisions that you have to make to encode your data in one of these NoSQL systems. What becomes the key, what becomes the value? Are the blog posts nested under the comments, or the comments nested under the blog posts? Right? Do users keep their own wall, or do the the messages on their front page, or does the person who wrote the message keep access to it, or both? Right? All these different design decisions of nesting layers and so forth complicate integration and complicate standards. Okay. So it's a tough sell. The other point that I guess I like to make that's related to this third one here is that there's no real free lunch, right? Either the complexity is going to be in the system that you use to model the data, or you're going to sort of hand it over to the application. But in some sense, they're always these schemas, right? This application business model is going to be encoded somewhere. So having it centralized in the data system, as opposed to hidden more than once in various applications that access the data system, seems like a good idea. Okay. Okay, so I want to talk a little bit about this system PIG, and there's a couple of reasons for this. One is it represents this language layer on top of MapReduce, which I think is pretty important, as I've mentioned before. And it also represents a more direct interface to relational algebra, which I've argued is really the important abstraction from databases. SQL happens to be sort of intergalactic data speak, and is the universal language for programming databases and manipulating data in databases. But really the secret sauce and the technology that makes it effective is this underlying formalism of relational algebra. And PIG and a few other systems sort of expose this as a first-class citizen. And it's not necessarily the only way to do it, or necessarily the better way to do it, but it does. But since you can see the relational algebra directly, I think it's a nice thing to be familiar with. Okay, and it also, I think, makes the point that you can cherry pick a little bit what features you bring. So while it's very obviously inspired by relational algebra, and of course, if you look in the sort of people that developed it, you can see why. It definitely changes some things about the relational model, and I think that's an important point too, is that we can use this relational algebra abstraction independently of some of the systems that it came from. We can make whatever changes we need and keep what we like and throw out what we don't like. And so I want you to sort of put your relational algebra goggles on and see the world in terms of relational algebra. I think it's pretty effective for working with not just data in general, but especially big data, and reasoning about very scalable algorithms. Okay, so fine. So what is PIG? So PIG is a engine for executing programs on top of Hadoop. Okay, so you're going to write a program in PIG, and it's going to generate a sequence of MapReduce jobs that implement that program. Okay, and the language here is called PIG Latin, and it's an Apache open source project, and you can read more about it. Okay, and so why bother doing this? Well, if you're a MapReduce programmer, you're happy with MapReduce, why would you bother doing this? Well, suppose you have data in one file and data from websites in another. User data in one file and website data in another, and you need to find the top most visited sites by user in a particular age range. And so if you're thinking in terms of SQL, you can probably think about how to express this task as a query. And here's a pictorial representation of it that sort of shows a kind of data flow here. We're going to load users, we'll load the pages, we'll filter by age, do some kind of join on name, group, count up the clicks, order by clicks, and then take the top 5. This may or may not be the way you draw it on the whiteboard if you were to express it yourself, but it's a reasonable way of describing the problem. Well, in MapReduce, there's 170 lines of code, and at least in one example coming from the papers here, it took someone 4 hours to write it. These kind of metrics of how development time are never too compelling, because it kind of depends on their background and their skill set and so on, but still a decent amount of time. While the same program is in PIG Latin is just 9 lines of code and takes at least in this case, 15 minutes to write. And further, does sort of capture some of this more abstract description of what's going on. Now, this is a little bit contrived because these boxes obviously correspond to sort of particular pig commands. But I'd argue that this, even people that don't know pig, if they were to ask sort of what the tasks are in evaluating this English question, they might come up with something along these lines. They may or may not say join, but some of these steps would be present. So I think you could wave your hands a little bit and say that it captures a little bit of the natural language description of the task. Okay, you may or may not buy that. Fine, so here's what it looks like. Load the user data according to a particular schema. Filter the user data based on the age range. Load the pages data. Perform a join. Group. Then you say, well, for each group, count the number of clicks, and we'll talk. This one probably looks the least like relational algebra, and we'll talk about it. And then sort the thing, and then just take the top 5 and store that result into a new file. Okay. And so the point here is that you could also think, well, boy, I could just write all this in Python, right? That'd be much easier. Why do I need to use this new language? Well, the point is that each one of these steps, well, not each one, groups of these steps correspond to individual MapReduce jobs, which mean they scale really, really well, right? It doesn't matter how big your users table is, and it doesn't matter how big your pages table is. This program will work. Okay, so how does the system work? Well, the programmer is going to enter a Pig Latin program by writing these commands and assigning the results to variables, and then you can refer to the variables in future commands. So this is, we've loaded data into this variable A, loaded data into this variable B, and then you can filter by reference to A and store the result in C and so on. Okay, and then we'll make this point again later, but nothing actually happens. No work is actually done until you try to actually write out the result. So this is sort of what we call lazy evaluation. All right. So fine. So what happens when you write this program? Well, the pig parser will turn the syntax of the program into an abstract representation of the program called an execution plan. And so this is using parlance from databases. And the lead of the pig project is a great database guy named Chris Olson. Okay. So this abstract representation of the plan, these operations that I'm going to call operators, again using database parlance, are sort of one-to-one with the commands, although they need not always be. Okay, but we're not done there. That's just the execution plan. It's still sort of abstract. We can't actually execute that. What we need to do is compile that down into MapReduce jobs. And the gain here is going to sort of be to minimize the number of MapReduce jobs you need, because there's a lot of overhead to executing one of these. So you don't want to run a whole MapReduce job just to filter a data set. You might as well lump that in with other work that you're already doing. As long as you're scanning the data and reading off a disk, you might as well do as much as you can with it. And so, for example, in this case, this program can all be implemented as just one single MapReduce job. In the map phase, you load the data, you filter it, and you also load the other data set. In the reduce phase, you do the join. Okay. And we'll see another example of this a little later on. And then finally, these MapReduce jobs are scheduled on a Hadoop cluster as usual and run as usual. Okay. So these performance results are a little funny, but I still like the argument being made. This is Pig performance versus MapReduce. Okay, so this is a little funny because Pig is built on top of MapReduce. But the point is that the first version of Pig in September 11th, 2008 was a lot slower than just writing the thing raw against MapReduce. But with some various improvements, it got better and better over time until eventually it was just as fast as the handwritten MapReduce. And I think you see this sort of pattern quite a bit, that there is a cost to abstraction, but that you typically can recover a lot of the performance of the hand-coded stuff, meanwhile having gained some measure of programmer productivity by offering a higher level interface. Okay. And so I just like the fact that they actually just bothered telling the story, that admitting that they were quite slow in the beginning and got faster over time. Okay. All right, so what's the data model here? So there's 4 types involved here. One is the atom, which is just a primitive, right, an integer, a string, and so on. And then there's three different collection types. One is a tuple, and these should be familiar from our first assignment we worked with Python, right? So these three all exist in, well, I shouldn't say that. Actually, bag is a little funny to think about in terms of Python. Let me just say, the first is a tuple, which is a sequence of fields, and every field can be of any type. They need not be atoms. Okay. And then there's a bag, which is a collection of tuples, always tuples, but those tuples need not be the same type. So this is different than a table, different than a relation. Okay. And it's a bag, not a set. And, I guess I can ask you, what's the difference between a bag and a set? Well, a bag allows duplicates. And then the third type is a map, which is a little bit confusing because we're talking about MapReduce, but this is a dictionary in Python, right? So string literal keys map to any other type. Okay, so let's look at an example of this. So what is this thing? Well, it depends on my notation, I guess, but assuming that you don't mind my angle brackets referring to tuple, then you can see that this outer thing is a tuple, and it has three fields. It has a integer, which is just an atom, and then it has this thing, which is a bag, the curly braces I'm going to use to indicate bag, and then it's got this thing, which is a map, a dictionary, that has just one element in it, mapping the key Apache to the value search. Okay. So let's name these guys F1, F2, and F3, and we'll point out in a couple of slides where those names can come from. There's a few different places they can come from, and I'll point out one of those sources soon. But right now, just assume that we have them. Okay. Okay, so let's consider these expressions over this type. So we can write $0, and what that means is give me the first field in the tuple. All right, so in this case, it's just the number 1. We can also access it by name. So if we access F2, that will give us the second field, just because we gave it that explicit name. There's nothing magic about F, nothing magic about 2. And that'll give us a bag with these values in it. By the way, we should say, what are the elements of this bag? Well, they're tuples with 2 integers each. Okay. Now you can also access F2 to give me, so what does this expression do? Well, F2 gives me the bag, and then you can write $0, and I don't love this notation. It's a bit of an abusive notation, but what it means is for every element of the bag, project out the first element. And so this will give me another bag, but it only has 2 and 4 and 5. It has the 0th element of every tuple. Okay. Then you've got this magic hash symbol here, which means find me the value associated with the key I'm about to provide. So look at F3, which is the third field, and hash into it and give me the key Apache. If it's not a map, you're going to get an error. But in this case, it is a map, and so what gets returned is the atom search. Okay. And then you can also write functions. You can say sum up all of these values, and this expression is the same one we saw here, which will be a sequence of integers. And so that'll give you 2 plus 4 plus 5. Okay, and there's a few different other ways to sort of manipulate these things. But the first thing to note is that this is non-relational, right? You've got these nested data structures, and you've got a few different data types. All right, so let's go over some of the commands in Pig. So the first one is load, which is how you get data into the system. And here the data is on HDFS in a Hadoop cluster, and the logical data model, each input data set is assumed to be a bag, which is a sequence of tuples. Okay, so you can specify, you can just say load, but you can also specify the function you're going to use to parse the data with this keyword using. And this seems like sort of just a trivial implementation detail, but it's actually kind of an interesting point and really gets to the heart of one of the problems with many database products, and one of the advantages of these MapReduce-based systems is that sometimes you're presented with data that's in its raw form, and you need to parse it yourself. Okay, and so the database value proposition is, well, look, design a schema and load all the data into the schema, and after that you'll be able to get all these benefits from querying. Well, look, who's going to do that loading task, right? That's a big parallel job. If I've got 20 terabytes of text files, somehow I've got to manage that computation. And so this is where Hadoop and also therefore Pig and Hive come into play. And so a lot of times what you'll see is that the application for a, say, data science system, data science application will be architected where Hadoop and its extensions are being used to do the initial processing, parsing, and loading. And then the result of that is loaded into a more conventional database for kind of ad hoc querying. And we saw this in the very first segment. We talked about the Obama campaign using this architecture as well. They, at least in an article, you can sort of infer that they had used a similar article. They mentioned Hadoop for the ETL workload, extract, transform, load, another piece of jargon, and then they mentioned this Vertica database for the slicing and dicing. Okay, and you see this. It's almost becoming a standard. I hate to use the word standard, but it's a best practice in designing these kind of data analysis architectures at scale. Okay, so fine. So what's nice about this is that you can specify your own parsing function, so you can work with data in its raw format. All right. And then further, you can specify a schema. If your parsing function is capable of producing lots of different things, you can say, here are the names of the columns that I want to supply. So this is one source of where these column names are going to come from, is you specify them right there in the load command. So this is kind of schema on read, if you will, right? There's no schema associated with the data. It's not self-describing, but you can impose a schema on it as you read it into memory. Okay, fine. And so maybe this is what we get back. We get back a sequence of tuples, and we'll use this as a running example. All right, so the next command is filter, which is pretty simple. You just get rid of some of these tuples, and you can have arbitrary Boolean conditions. You can do kind of regular expressions because everything's very text-based in the Hadoop world, which is in some cases a limitation. And the syntax looks like this. You say filter some big data set by some condition. And so in this case, filter where F1 equals 8. And remember that F1 was the name we gave it in the load command, the name we gave to the very first column. And so this finds all the tuples where the first position is equal to 8. Fine. So the command is group, which is bringing data together. Okay, and so there's a couple different forms of this. But we're going to focus on, so this, just right now we're just talking about group. Okay. There's a co-group command that I'm going to talk about in a moment. All right, so group says, group this large data set by some sequence of columns. Okay. So this looks a lot like the SQL clause that's the same, it got the same sort of flavor. But it does something pretty different. Okay. So if this is A and we group by F1, well, what we get out is tuples, but now the first column is the same because we grouped by F1, but the second column, the second field, I should say, is now a bag, a little group representation of all the tuples that were associated with this particular key. And so if you look over here, there's only one tuple with 1, and that tuple appears in the group. There's 2 tuples with F1 equal to 4, and so this bag has 2 tuples in it, and so on. Okay, so this is how you can start off with something that's kind of a flat structure, and you can build up a nested structure for various reasons, and we'll see why. Now, the other thing to keep in mind, and this is another thing I don't really love about Pig, because they're doing things sort of implicitly rather than explicitly, is that the name of this field, every field ends up having to have a name, and so the name of this field is defaulted to the name group. Yeah, sorry, I just lied. The first field is defaulted to the name group, and the second field is defaulted to the name of the original data set. And so I find this a little confusing when you're writing Pig yourself, but you can sort of see why they did it. The reason is that just these bags all together actually have the same information as the original data set, just nested in a certain way. And so calling it A sort of makes sense. It's got all the same information. So for example, notice that the value 1 is now repeated twice, once in the group and it's still in the tuple. Okay, so fine. So there's also a command distinct that does just what you might imagine. It gets rid of all duplicates. And just for a simple example here, if you've got 2 different elements in the bag that have the same value, your output will be this. Okay. I might make a claim that distinct A is equal to grouping of A by all three columns at once. So first of all, why am I making that claim? Well, remember that the group operator puts out a single tuple for every unique value of the grouping columns. So that sounds about right. And you can also maybe think from if you know SQL, that this is sort of true there, right? You can use this distinct keyword in SQL, and you can also group by all the columns, and you'll end up getting the same result. So are these two expressions the same? Do they produce the same output? Well, not quite, because the grouping structure, the group command produces a group field, which is now the whole tuple, excuse me, and the A field, which is a bag with a single tuple in it. So you get this sort of repetition of information, so distinct is much more concise. So you need to be careful and sort of make sure you understand what these things are going to produce. So how does group work? Well, we already saw, going back to our MapReduce schematic or our parallel processing schematic, we break the data into pieces. We apply a map function that assigns each tuple to its key and groups the tuple in the value as well. And so here, if we group by F1, then F1 becomes the key, and the value is all three of the elements in the tuple. And those are shuffled across the network to the reduced side, and the reduced side will construct this bag type out of the set of tuples. Okay, so this is a single MapReduce job. All right. So the for each command is almost certainly the most complex one. So here you're basically going to manipulate each tuple in a bag. So you write it like this. You'll say for each A, generate something. And here we're generating a tuple with two fields. One is F0 and one is the sum of F1 and F2. And here you can call user-defined functions, or you can write other kinds of arithmetic expressions. You can sort of do lots of things. Okay. Fine. So another example is first we group A by F1, just like we did in the previous slide. Excuse me. This should be Y. And then for each Y, generate group. So what's group? Well, remember that's the magic name assigned given to the group field. And then Y, which is the magic name given to the bag field, dot a list of projection columns. And so this is the second element and the third element from each of those tuples. Okay, so what does this look like? Well, X, which is this first element here, well, we get the first field from A, which is this column here, and then we get the sum of the second two. So 2 plus 3 is equal to 5, 2 plus 1 is equal to 3, 3 plus 4 is equal to 7, and so on. Okay. Then down here for Z, remember that Y looks just like it did in the previous slide. Here. Oh, well, no, sorry, I didn't actually do the complete example of Y. So Y is all of A grouped by the first field. But then we're going to generate the grouping field, which is the same. And we're going to project out the second two columns. We're going to ignore the first column in each one of the bags. Okay. And so the point here being that you can manipulate these nested objects by writing these kinds of expressions. But I think the other sort of lurking point here is that it's a little bit complicated to think about what's going on because of this extra flexibility you get with the nested data model. Okay. So you'll get a chance, in the assignment, you'll get a chance to try some of these out and make sure you understand what they're doing. Okay, so then there's this keyword flatten, and it's not really its own operator. You use it in the context of for each. And so here, because of the complexity here, what you might really want is, look, I just wanted to get rid of the, if you want to recover the flat version of the nested structures created and stored in the variable Z, well, you can do so like this. for each x, generate group and then the flatten of x. And the result you'll get out here is, but regardless, what it does is sort of peel out this bag and produce an extra tuple for each. And I don't really like this because it sort of changes, just using the keyword flatten changes the semantics of the for each and generate. And I think it's a very, very confusing way of doing it. So the idea, it's hard to explain the principle going on here, just sort of memorize what it does. Practice with it and memorize what it does. All right. Okay, so let's take a look at the cogroup command. So we've seen the group command, which we're showing a single data set, and the cogroup command does the same thing on multiple data sets. And we've seen this mechanism before when we talked about MapReduce, but here in Pig we make this operation explicit and give it a specific command, and we'll try to see why that is. Okay, so the syntax looks like this. You say cogroup a data set by some field reference or multiple fields, and here we're referring to a field by name, and here we're referring to a field by position, as we've seen before. And so if this is A, a bag of tuples, and this is B, a bag of tuples, then the cogroup of them looks like this. So now we have a group field, and we have a data set A, a field named A, and we have a field named B. All right, so we still have the same grouping key, but we have two groups associated with it, one from one data set and one from the other. Okay. So a couple things to point out. One is if there are no tuples from one of the data sets, then it just gets the empty group. And here you see an example from B. And then the other thing to point out is this is a little different than what happens in MapReduce directly, where what we showed with the join operator with MapReduce is that you could use the join key to sort of co-group two relations, and then all of these tuples would all sort of appear in the same group in the reducer. But here we sort of make it explicit to make it two separate groups. Okay. Fine. So I want to come back to cogroup in a second, but first let's talk about another operator which is just called join, and so it does exactly what you'd expect. So join, you say join A by some set of field references and B by some other set of field references. Okay, and given A and given B, the result will be what we've talked about in the past, which is, you look for the first position of A, $0, and find all the corresponding first positions of B. So here's 1 and 1. So we have 1, 2 from A, and 3, 1, 3 from B. Okay. So there's nothing stopping you from having multiple data sets out here. As many as you want, and they can all be sort of processed together. And so you can think about what's going on here is that this is one MapReduce job underneath the sheets, where in the map phase, every tuple from a variety of data sets is all being associated with the join key, represented by this field reference in the syntax, and then shuffled across the network to arrive at the reduce phase. Okay, so here's what it looks like. Well, if we have multiple relations represented by colors here, green, blue, and red, well, they can all be processed by the map phase and associated with keys, shuffled across the network to produce the join tuples here. Right, so there's nothing fundamentally binary about this operator. Right, it's just processing tuples associated with the respective join keys and shuffling them all across the network. What can go wrong with this basic mechanism of associating tuples with the join key, shuffling them across the network, and then producing computing the join on the reduce side, which is what we did in the assignment as well. Well, so one example might be if one table is very, very large and the other table is very, very small, there's an opportunity to do something much, much faster, which is replicate the small table across all partitions of the large table, which allows you to do all the work in the map phase. Okay. The second sort of special case here is a skewed join. What I mean by that is if there are many values in one table that join with many, many, many values in the second table, then you'll end up with one reducer doing most of the work, and the effects of parallelism get sort of washed out. And then the third special case algorithm is to do a merge join. And so this takes advantage of the fact that you may have already grouped two relations in the same way, such that you know for sure that on a single machine, I've got all the tuples I need from one relation and all the tuples I need from the other relation. Okay, so let me see if I can make this more clear in pictures in the next few slides. Okay, so for a replicated join, the situation is we have one large table broken into pieces and one much smaller table. And so what we could do is just shuffle all these tuples across the network and do the join in the reduced side as we do normally. But there's an opportunity here that says, well, look, if this thing is small enough to fit in memory on a single machine, why don't we just copy it, send it out there to every map function that wakes up, we'll go pull it across the network directly. Okay. Then we have all the information we need right here in the map side. Every one of these tuples can be joined with corresponding tuples in this partition. Every one of these tuples can be joined with corresponding tuples in this partition, and so on. And so at the end of the map phase, you end up with the right answer, all the joined tuples for, this sort of blue A and this red B. Okay. And so why is this cheaper? Well, we didn't have to shuffle everything across the network. We did it all in the map phase, and it makes a huge difference. Okay. So you might see this called a broadcast join as well. So the small relation must fit in memory, and the idea is that each mapper in the map function pulls a copy of the small relation directly out of HDFS. Okay. All right, so for the skew join, the situation is as usual. You got two relations, this sort of blue one and this red one, and the map phase associates each tuple with its join key. But the problem is that most of the data ends up on a single reducer, and the reason is because maybe most of the data here is associated with a single join key. Okay, so for example, if you're joining on order ID and line item, you're trying to associate all line items with their corresponding order. It could be that one order had millions of parts and all the other orders had 5 parts or so. Okay. So if a significant fraction of the overall data set is associated with a single join key, then this reducer will be doing all the work, and there won't be much benefit to parallelism. Okay. So this would work, but there's a problem. So this is from a former student here at UW who did some work on this problem. And this plot shows time in seconds on this x-axis, and this is just a list of all the tasks. And so you see that the reduced tasks here, they can't start until all the map tasks are finished. Okay. And the map tasks mostly finish quite quickly, sort of maybe 20 seconds, but one or two of these map tasks take a very long time, sort of on the order of 270 seconds or so. Okay, so all this space in here is sort of wasted work. There's a couple of problems here. One is fundamentally a map reduce. In many applications, you logically actually could start doing some work early based on the map output that's already been finished, and that's just not the way map reduce is designed. You can't it's not designed to be able to take advantage of those applications because you can't guarantee that it's safe to do so. So for example, if you're adding up numbers, you could start adding up in the reduce phase, you could start adding up numbers early. But if you're doing something more complicated, you may actually need to wait for all the results to be present in order to get the correct result. And so since they can't guarantee that it's safe, they make you wait. Okay, so fine. So this skew problem ends up sort of killing parallelism and turns a job that could take sort of 50 seconds into one that takes 350 seconds. And it's not even significantly longer than doing this sequentially. If you sort of added all these pieces up, well, I shouldn't say that. This is still worse in sequential, but you certainly lose a lot of your bandwidth in parallelism. Okay, so one task might take 5 times as longer than the average, and so there's little benefit. And so one takeaway here, so I'll tell you what one way to partially solve this problem on the next slide. But the takeaway here is if someone asks you what the one of the biggest performance bottlenecks of MapReduce is, you should say stragglers or skew. Skew is more of a term for this in the database community, but stragglers is maybe a little bit more common. Okay, so this is a straggler task that takes a lot longer. All right, so what can we do about this? Well, here's the situation where we had a lot of keys that all ended up on the same reducer, and this guy's taking too long. One thing we can do is split this data up into more reducers. So allocate a few more reduce tasks and move that data over here and split it into 3 more. Now, broadcast that little red relation, right? So I made it disappear from over here, recognizing that this is perhaps small, and replicate it to all 3 of these reducers. So it's sort of a combination of the replicated or broadcast join and the regular reduce side hash join. Okay. So now you've got 3 reducers working on this problem as opposed to just one, and you get things a little bit more balanced. And so this skew join is something that Pig can do if you specify it. All right, it won't do it automatically though. So fine, and so now we get our entire joined relation, which is what we want. So finally, merge join is the 3rd special case. And this is, let's see, so the first special case was an opportunity to do things much faster if one relation was very large and the other relation was small enough to fit in memory. Skew join is more of there's a problem that can occur and you need a special trick to be able to address the problem. Merge join is more like the former. It's looking at an opportunity to use a more high performance algorithm when certain conditions are met. And so what are those conditions? Well, when you recognize that the red relation and the blue relation are already been co-partitioned on the appropriate join key, right? Then the map phase alone has enough information to just compute the join itself. It doesn't actually need to assign it all to assign each tuple to a join key and shuffle it across the network, right? So you know that all the line items for a particular order, for every order that's here, all of its line items are also here on this machine. If you know that to be true, then you can do it in the map phase. Okay. So the question may be, when is that true? Well, that's when we go back to the cogroup operator. It's possible that you've already partitioned these 2 tables on the appropriate join key because of a previous command in Pig. Okay. And so it can be aware of that and use a merge join. Sorry, I say be aware of that. You still specify explicitly that you want to use a merge join, but so Pig's not doing that automatically, but you can take advantage of this situation when it arises. All right. So since each mapper already has local access to the records from both relations, they're already grouped and sorted by the join key, you can just read in both relations from disk in order and compute the join. All right. So we have this cogroup operation and we have join operation. Why do we need both? Well, the reason to make cogroup explicit is that if you think about it, join is really a 2-step process, right? There's one step to create the groups based on the join key, and then a second step to actually produce the join tuples. But that group creation step is useful for a lot of applications, not just producing a join. So for example, if you want to cogroup and add up all the contributions from each relation, you can do that in a single step. You don't need to sort of join the tuples first, then do another grouping afterward, which is something you would have to do in relational databases. So that's a chance to take what would be 2 MapReduce jobs and combine them into just one. Okay. And so here, I guess the example is if you want to just count the tuples. Okay, so, but, what to point out here is that you can express join. Join is essentially just syntactic sugar. You can express a join in terms of cogroup. First step is to cogroup on the same column, on the join columns, and the second is to run this for each command that would generate a flat view of results and revenue. Sorry, I guess I should say A and B here. That's sloppy. I changed the names. Okay. Fine. So other commands that we're not going to talk about in detail are store, which writes data out to HDFS, so it's available for future commands. Union, that combines 2 data sets together and removes duplicates. Cross product, which finds all possible pairs between 2 data sets, which can be useful if you're about to compute some sort of similarity function, as we talked about. And then dump, which prints output to the screen, and then order, which sorts the output. Okay. So as an example of store here, remember you can also, just like you can use your own custom function to parse data, you can also use your own custom function to write it out. Okay, which means it allows the data to be more compatible with, say, some other system that you're using, say MapReduce itself, or some other application that expects data in a certain way. And so that's, again, I sort of stress this with the load command as well, but this is actually pretty powerful and a pretty big difference from this, walled garden approach that relational databases take, where everything sort of goes in and then it's under complete control of the database. This sort of has more permeable boundaries where you can kind of have data lying around in whatever format, and you're still able to process it with Pig, but you can also process it with other systems as well. And so the reason this is crucially important is not just sort of a performance optimization for reduced load time or something, although sometimes that can help as well. It's because this data is too big to move nowadays, right? You can't put it all in the database and then suck it all out and move it over to some other system for working with. It's just too big. You can't move a petabyte, right? You have to bring the computation to the data as opposed to bring the data to the computation. Okay, and so these abilities to work with in situ data, produce sort of in situ data is emerging as a sort of a key requirement in this big data era that was not such a key requirement in the sort of era of relational databases. Okay. So let's consider an example of a Pig program and see how expressing the program in terms of these high-level operations offers optimization opportunities that the system can exercise unilaterally without the programmer having to specify it. Okay. So in this example, we're looking at traffic, weblog traffic data with sort of 3 columns here: the IP address, the time, and the URL being accessed. Okay. And so in the first step, we load the data, and here we don't need to use the using clause to specify our own parsing function because presumably the traffic.dat is in some format that Pig already natively knows how to parse, so some sort of simple delimited format. Okay, so it's expecting to find 3 columns, and if it doesn't, it'll be an error. All right. So the second command is group, so we group A by IP address. And then third, we say, well, for each of those grouped tuples, I just want the IP address and I want the number of weblog entries associated with that IP address. Okay. So this is counting the number of accesses by particular IP address out there on the internet coming in. Okay. And the next step, well, maybe in this particular task, we're only interested in sort of looking at traffic that originated from 2 particular gateways on our local network, and so we filter for just those IP addresses with the filter command. And then we store the result into a file on HDFS. And so the observation here is that, if you look at this carefully, you can see that as written, this is somewhat inefficient, right? We load a very large data set. We apply a grouping operation to a very large data set. We do some manipulation of those groups across the very large data set, and then we filter it down to something that's much smaller because we're only interested in these 2 IP addresses. Okay. So what would be nice is if we could apply the filter first. And so one thing you could do is just rewrite this program, and in this case, that's probably reasonable. You could probably notice that this was going on and rewrite it yourself manually. But in a more complicated program, you may or may not. And this is not the only example of an optimization that can be done. Okay. And so what Pig will do is actually move the filter automatically beforehand, before the group, and use, I guess I didn't modify the program here. I modified the abstract plan. It won't actually produce the text here. The ASCII is done. Remember we talked about an execution plan, and then it'll manipulate that. And so it moves the filter beforehand because it knows it's safe to do so. And this is, again, I keep coming back to this, but this is the one advantage of a high-level language might be that it's easier to express your program in. But that may or may not be true. In many cases, it could be actually harder to express your program in terms of these, limited operators. So, you might prefer kind of a general, a Java programmer might prefer a full-width Java interface where they can just write whatever code they want. But the point is that if you can, tie one arm behind your back and express your task in terms of these operations, the system can take over and make manipulations that it would be very difficult for it to do if you wrote in a lower level language. Okay. Fine. So the other point to make here is that, remember, this is what we call lazy evaluation. So when this command is executed, that's when it makes that's when it has an opportunity to apply these optimizations, right? So it did nothing but sort of build up your execution plan as you were executing these commands. It didn't actually do any work. And then finally, when you say, okay, now I really want the result, it can say, aha, I see your list of sequences, or sorry, I see your sequence of commands. I'm going to do some manipulation of those to figure out the right way to execute these commands before I produce the result. Okay. Fine. So we're not done. We now have to map this abstract execution plan down into a sequence of MapReduce jobs. And so the way it does this is it first identifies all the group and cogroup operators in the plan and assigns an individual MapReduce job to each one of those operators. And then incrementally what it's going to try to do is walk forward and backward and put as much work as it can into the same MapReduce job. Okay, so the group command needs to be its own MapReduce job because it's going to shuffle things across the network. But filtering, I could apply the filtering condition as I'm loading data off of disk, or as I process a tuple. I can check its condition to make sure it's from one of these IP addresses before I actually apply the group. So I might as well do that in the same MapReduce job. I don't need a whole independent MapReduce job just to do that. Further, the load command is just reading things off disk. It doesn't actually do anything difficult at all. I can put that on the same MapReduce job as well. And so it ends up with this one map function that's going to look something like, as you process a value, it's going to say, parse the data and then it's going to say if val.ip equals this, or val.ip equals this, then emit IP val, or val.ip val. Right, so this little program essentially gets generated by the compiler as just one map function and then gets executed. And on the reduce side, you can do a couple things. You can construct the groups, but you don't actually care about the groups because you're immediately going to count the results. And so it's smart enough to see that group plus for each is really going to just produce tuples like this, IP and count, and not IP plus some big group. And that's actually pretty significant savings because constructing these objects and sort of passing them around is pretty expensive. So you don't actually need them. You don't want to use them. So there's sort of two levels of optimization here. One is it moves operators around, which I like. So you got this algebraic flavor. And two, it compresses logical operations into single physical operations. And the overall name of the game here is to reduce the total number of MapReduce jobs being executed because they're expensive. Okay. And then finally you can write the things out, and that can also happen in the same reduce phase. So this entire task ends up being just one MapReduce job. In other cases, you may need to just do sort of multiple groupings, or you may need to sort, or so on, and each one of those requires its own MapReduce job. So for example, certain commands always require MapReduce job, like sorting. Okay. So what did we talk about in the last several segments? Well, we described NoSQL systems and argued that they're important for a data scientist to understand, in part because you may be using them, but also because you may be asked to weigh in on their relative strengths and weaknesses compared to other systems. And so we talked about NoSQL sort of meaning no schema and no transactions and no language, and maybe less specifically about SQL. And overall, they're kind of a reboot of data systems, zeroing in on just high throughput reads and writes. Okay. Right. And so now the design space of these large scale data systems is sort of being more fully exploited with different permutations and combinations of particular features. But overall, there's a clear trend back toward reintroducing schemas and transactions and languages and so on. And so we talked about Google's spanner system as an example of this trend. So NoSQL is not, it's an evolving sort of concept. The main thing to realize is that the entire space of possibilities in large-scale data systems is being explored, and NoSQL represents one segment, relational databases represent another, and there's new segments emerging. So you might hear the term NewSQL, for example, which is kind of a re-architected database that does try to achieve some of these other features. Okay. So fine. Then we talked about Pig in particular as an example, not so much of a NoSQL system, but as a analytic system that puts a layer on top of MapReduce. And we chose Pig because it has this relational algebra-like layer on top of Hadoop. And so I want to make the point that relational algebra comes up in a lot of different contexts. And in this one it's a little bit interesting because although it has a clear relational algebra flavor, it's not actually a pure relational data model. You got these sort of nested structures. And the point here is that you can kind of cherry pick some of these concepts and techniques pioneered by databases, and you don't necessarily have to use them in the context of databases. So you don't need to sort of throw the baby out with the bathwater if a database doesn't appear to be meeting your needs. And these systems are sort of doing that. So as you review different systems emerging as a data scientist, you can start to understand the particular set of features they offer and understand the provenance of those features and the history there and the pros and cons therein. Okay. And so Pig also, one takeaway of it is that it has this sort of schema on read flavor rather than schema on write, meaning that you can work with in situ data. Okay, and I mentioned this a couple of times. I just wanted to point out that that's really one of the new requirements associated with maybe NoSQL as well as even SQL-like systems, is that you have to be able to work with data in its kind of native format. And the reason for that is it's just too big to transform all over the place. All right.